alacağım. Orada uğraşabilirsiniz.
Hocam adı da konuşmacının kendisi görünmüyor kamerası.
Kendisinin mi? Sağ taraftan şeyi ayarlamışlar. Standart. Geliyorum. Bir saniye şunu Bekir Hoca'ya vereyim.
Siz yemeği isterseniz. Sormadan gidin.
Gidin. Siz yemeğe gidin. Bir şey lazım.
Aha, ben buradayım hocam. Yedim geldim.
Gidin. Koş.
Yok sabah.
Sabah.
Bekir Hocam.
Aldım.
Post sizde Sayın Hocam.
Şimdi diğer arkadaşlara nasıl
Bir saniye.
vereceğim?
Sadece
Şey mi
sesimi açayım.
yapacağım?
Sizi duymuyorum şu anda. Özür diliyorum. Sesi vereceğim. Buyurun Sayın Hocam. Bir daha konuşur musunuz?
Şimdi ismini
Niye
okudum
ses
arkadaş
gelmiyor?
nasıl direkt açabilecek mi o?
Sesiniz gelmiyor Sayın Hocam.
Gelmiyor mu? Açık benim şeyim. Bak burada ben görüyorum sesim açık.
Bir saniye hocam. Ses. Şimdi gelin.
Geliyor mu sesim?
Tamamdır hocam. Teşekkür ediyorum. Buyurun Sayın Hocam.
Şimdi
Başlayabilirsiniz.
konuşmacılara nasıl hak verdim de onlar açabilecek mi direkt kendi ekran
Evet.
paylaşımıyla?
Hocam onlar direkt şehir yapabiliyorlar. Onları hiç siz şey yapmasanız onlar şehir yapabilirler. German Bey yapabilir.
Tamam.
Tamam.
Peki cevap falan geldi mi acaba?
Hocam yan tarafta sizin
Şey
o
görüyorum şu anda.
kişiler sekmesine tıklar mısınız? Yan tarafta sütun açılsın. Şu katılımcılar kısmına tıklayın hocam. Yan tarafta açılacak. Sol tarafta ya da sağ tarafta. Liste açılacak.
Açtı şu anda German var sadece.
Evet, sadece German Bey'le başlayabilirsiniz hocam. Diğerleri de gelecek sonra.
Tamam o zaman.
Herkes kendi saatinde giriyor Sayın Hocam.
Ama şu anda zaten geçmiş bulunuyor. 13.40.
Evet. Evet, başlayabilirsiniz
Geçti
hocam.
onlar o zaman.
Evet, başlayabilirsiniz Sayın Hocam. Yani giremediklerini söylediler ama biraz geç kaldık. Şimdi
Tamam.
girerler tekrardan. Biz onları arıyoruz şu anda. Siz sırayı
Erman,
değiştirebilirsiniz
duyuyor
Sayın
musun?
Hocam.
Yes, I can hear you. Sure.
Erman,
Yes. Let me see.
okay. First speaker, you are first speaker because
Oh.
of the maybe Juma Friday prior. We are a little bit late. Sorry
Okay,
for
then-
this delation. Okay, I will start with you now.
Let me
I
transfer
would
the
like
talk.
to,
One moment.
yeah, I
Because
would like to invite one of my friends, German de la Funte. He will talk about the laser induced reverse transfer.
but let
Okay,
me transfer
Erman, you
the
can
talk
start.
to this. Yes, I'm transferring the talk because on my computer where I have the talk, I
Okay,
have a problem.
wait, no problem. You
I
can
have a problem with the
just-
connection. And
just sharing of screen.
yes,
You see at the green light.
yes,
green
one
color.
moment. Yes, one moment, because I need to. Let's see. Okay, I'm trying from here. I'm connecting from my other computer because it will go better.
Okay.
But I hope the connection is edu-ROM, so I hope the connection doesn't go bad in the middle of the talk. Okay. Not very good. Okay. Okay. Let's see. The other one is too doesn't connect. My other computer is too slow on the connection. So I try with this one, which is Ethernet. And okay. Almost ready.
Okay.
Okay, now I open and I close everything else. Okay. I think now it's ready. And now I can open my presentation. Okay, let's see if it works.
Mhm.
Okay,
Okay.
is it okay?
Yes, you can start.
Okay, sorry. Yes, sorry. Can you hear me well?
Yes, yes.
Okay, so I try to speak softly and well, not softly, intensely, but slowly.
Slowly, yes, yes, because of the new subject, and
Exactly.
maybe most of the people will understand if you go very slowly.
Yes, I will try. Just remind me if I go too fast.
Okay.
Okay, I
Okay,
planned so
I
that
will.
I could go at a slower pace than usual. So this is a lecture on laser-induced reverse transfer, or LIRT, which is some work we have done with our associated research unit in the University of Santiago de Compostela. I don't know how to get the pointer. If there is any.
You can use your mouse.
Yes, I try, but it doesn't. I don't seem to. Sorry, it just goes back. You see. I don't know if there is an option, but anyway. Okay, so this is done with the University of Santiago de Compostela, which has a research unit associated to our institute and the Research Council. And our institute is the Institute of Material Science of Nanoscience and Materials of Aragon, which is in the between Madrid and Barcelona in Spain. And it's a mixed institute with two patronage institutions, one is the Research Council, CSIC, and the other one is the University of Zaragoza, where our laboratories are. So Let me give you an outline of the talk. This would be, first I will say something about what makes lasers unique from other light sources. Then what are lasers like? Now, what do they look nowadays? They are very different from a few decades ago. Then how lasers interact with materials, and particularly paying attention to how melting and ablation and other phenomena take place in the interaction of lasers with materials. Then in a second block, I will talk about the laser-induced reverse transfer technique, about how the experiments are carried out, and give you some mechanistic considerations with indicating some potential applications that we may have identified. And then I will give some conclusions and outlook of this method. So first of all, I should thank the organizers for inviting me to give this lecture. This is what I should have said at the beginning, but I was too distorted by the informatics to make this work. So I thank the organizers very much, and Becky, who is here as a chair, for this invitation and for making the connection. And now let me tell you about what makes lasers unique and what do they look nowadays. Here you see two pictures. One is a high power laser, a 2 kilowatt laser on the left. It's a CO2 gas laser, and it emits radiation in the mid-IR spectrum, around 10.6 microns. This radiation interacts with very small bandgap materials. So it interacts almost with everything, with every type of material directly, except those which are very expensive, like infrared materials, such as zinc selenide, zinc sulfide, etc. On the right, on the other hand, you see a small laser. This is a typical laser that is used in the laboratory. This one in particular is a picosecond or a sub-nanosecond laser, which emits 9 watts of power. Remember, the one on the left is about 2 meters long by about 60 centimeters high and 60 centimeters wide, and it emits 2 kilowatts of power. It has a large cooling unit a little further to the right that you do not see, and this electrical control unit on the left. The one on the right, it has this very small control unit below that we don't see, but the laser is the size of the screen. So this is a big difference, and there are many lasers now which can be employed on many operations on materials that are really small, and they can handle them nicely. They are not expensive, and they're very they're portable in some way, or at least if not portable, they can be placed in easily in different areas, different places with robots, etc. So, lasers in their interaction with materials, you need to take into account what type of emission comes out of the laser in terms of wavelength on the one side. And so most common lasers that you can buy have emission around the UV, the visible, the near IR, or the mid-IR. These are most of the common ones, and the ones you see here listed are common commercial lasers that you can buy easily, with many of them with very high power. What the main difference is between a laser output and a normal lamp or the sun is the irradiance. And so we have a small, a relatively simple, straightforward calculation here of what the irradiance level is, let's say, outputted from an 8-watt pulse laser, and with 20 hertz, 20 pulses per second, and approximately 40 microns in diameter spot. And this is, or 80 microns in diameter. So this would give you irradiance value of 1.6 10 to the 12 watts per square centimeter, and the wavelength of 1064 nanometers. If you compare it to a 1 kilowatt tungsten halogen lamp, then this lamp emits in continuous wave mode. It emits between 400 and 2,500 nanometers approximately. And the best you can do with the best optics to make the smallest spot gives you a focus of 3 square centimeters, and that, if you calculate the 1 kilowatt, this is about 330 watts per square centimeter of irradiance. So you have about 10 orders of magnitude between an 8-watt power laser and a 1 kilowatt lamp. And this is a big difference between them. And the other difference is that one emits at the single wavelength of 1064 nanometers in the near IR, and the other one emits between the UV and the near IR around 2500 nanometers. So it has no selectivity from the point of view of the wavelengths. The one on the right, the lamp is not collimated light. The laser is collimated. It's a collimated beam, so you can really focus it very tightly. So this is the difference between a diffuse light source and a laser. If you consider from a thermodynamic point of view, what happens when a laser is irradiating a surface, when you have very, very low power, let's say like a pointer, which has milliwatts of power, then you just see a color on a surface, and the color may change depending on the color of the surface. So if you take a red laser and you put it into a yellow or a white surface, you will see it very nicely with a lot of contrast. But if you put it into a black surface, you will almost not see it. And that's already an interaction. That's already an interaction of this laser with the electrons. And it changes what you as an observer see in what you perceive as a color and a contrast. So, but if you go into higher powers, which is the objective of this lecture, then as you increase the power of and you go to a few watts of laser, then you can heat the surface where you focus the laser and change the temperature locally, as you see on this diagram on the left side. Then if you go to the next figure, this then where it says melting. So the first one is heating only. The next one is already heating and melting. And so you have a change of state from solid to liquid. And now by increasing the laser intensity, you have caused a change of state, an increase in temperature, and you have a liquid there. When you do this further and you increase even further the intensity of the laser, you can evaporate part of this melt, and now you see evaporation. So you have a vapor plume. So now you have a solid, liquid, and gas with the vapor from this liquid. It could be a metal, it could be a ceramic, it could be anything. And if you increase even further the intensity of the laser, then you can also excite the vapor plume into a plasma. And now you have the 4 states of matter that we view from thermodynamics, which is solid, liquid, vapor, and plasma. And in the plasma, there is a unique characteristic. The plasmas include species which are highly excited and move above the speed of sound. And as they move above the speed of sound, they generate shock waves. And so you have generation of shock waves with the plasma, and you can have much complex phenomena, as you see in the figure on the right, where you have a mixture of probably sublimation directly, that means direct sublimation of material, melt formation, vapor, plasma, shock waves emitting melt droplets, emitting parts of the solid which are broken up because their coherence is not sufficient to maintain them together. So you have grains, for example, in a polycrystalline material being ejected, etc. So this is a complex phenomenon. And that is what is called ablation. It's removal of material from a surface. And so overall, you can look at this ideal graph. And if you have a continuous wave source or a long pulse laser source, then you can heat materials and you can melt them, as you see on the left side of the graph. If you go towards short pulses and high intensities, then you reach ablation. You can have in the mid regime, you can have melting and ablation put together in a complex phenomena. But if you go extreme to the right towards femtosecond pulses, 10 to the minus 15 seconds, then you have pure ablation phenomena and low heating. So you can see an example here. The one on the right, it's cutting a metal with ablation. and the shock waves eject the melt that is formed on the cut. And so it's a very fast energetic phenomenon. On the left side, you have seen a typical industrial laser cut with melting and ejection via several atmospheres of pressure of gas. In there, you have to use the gas to eject the melt because the melt is very viscous. Otherwise, what you get is a cut and a self-weld. So you would not cut the material. But on the right side, there's no need for gas. And this is a very nice difference between melting and ablation regarding the energetics involved in these processes. So if we can see now, let's see if this goes through. Okay, now you can see something which is much less energetic and is not ablation, and it's probably not melting necessarily. I would not be able to tell you exactly, but this is a typical scan. This is what we call beam scanning. These most commercial lasers you can buy come with this, and they allow you to essentially print and move the laser as you will with a simple software program. So if you look on the right, these are pictures. Well, these are drawings basically that we made and we filled from essentially a CAD file. And you can see that depending on the intensity and other conditions of emission of the laser, we can get very different colors, and they're permanent. And this is a titanium coated ceramic. And what we are doing here is oxidizing the titanium at the surface. And depending on how we oxidize this titanium, whether the titanium oxide layer is thicker or thinner, then we, by the mechanism of color formation here, we can get the different colors and reproduce them. And this is a different type of phenomenon now that I show you here. This is with a femtosecond laser. That was with a picosecond laser. And there was a lot of thermal exchange, thermal input into the titanium. And that's why we oxidize the titanium, because we increase the temperature and oxidation takes place. Now, this is with a femtosecond laser. And here we don't really increase the temperature, or we hardly increase it, because the pulses are very, very short. They are femtosecond pulses, and there's not enough heat exchange with the material. And so we have a different mechanism taking place here. It's an interference mechanism between the incoming laser wave and the plasmon polariton wave generated at the surface of the material, of a conductor. In this case, it's a metal. It's a chromium film on an ABS polymer substrate. And you can see that you can get very well-ordered, long-range periodic surface structures. And this is what happens with them, how you can play with light. Now, as you change the angle of the observer and the illumination, then you can see a color change, as you see on this video on the right. And it's quite different from the previous titanium color, which was fixed from all angles. And the mechanism was completely different. This is how it is done. You can see it on the left. This is a commercial, coherent femtosecond laser that you can buy for a very nice price of probably about 200,000 euros. So this is another example. This is this is done with a femtosecond laser we have here in our laboratories, and this is with copper and with a green femtosecond laser wavelength at 515 nanometers. You can see you can get these diffraction gratings, which are very nice, and depending on the angle of observation and illumination, you can see all types of colors with high purity. You can also do microstructures and nanostructures. As you see here, you see the microstructure, but there is also a nanostructure built in there. And you can see that we can modify the surface properties of metals. And this is over stainless steel, I believe. And you can see that we have a super hydrophobic surface. You can see it even better on the right. You can, I don't know if you're able to see that. I hope so. I cannot, but I imagine you can see it. So this repels water because it's super hydrophobic. So you can really change the surface properties of materials using these lasers. And this is something that a lot of people in the world are working on. But now let me tell you about how we do other type of laser modification of surfaces. That's something which we have done more than anybody else. And we probably have pioneered, no, not for the first time, but in this type of application. And in this type of architecture. So this we called initially laser ablation backwriting, and then somebody in France called it laser-induced reverse transfer, which I think is a better name. And some other Japanese authors called it laser-induced backward transfer. So you can have your choice of name, but they're all the same essentially. And we have several publications which are interesting in the generation of optical waveguides. The first one was in Optics Press in 2006, and there are a few others. Some generating diffraction gratings also, and some analyzing what is really happening here. And this is the first type of experiments we did. You can see on the left some SEM. You can see there are different ways of depositing this, and it looks a bit strange. And maybe we can clarify it in a moment. And sorry, what you can see on the right here, you can see the diagram of how we do this. The laser is transparent to the glass substrate we put in on top on a metal target. And it does ablation on the metal target, and this ablation plume goes upward to the glass substrate, and that's how it interacts, and that's how it makes a coating or introduces nanoparticles into the glass. And we can do that selectively from the space and time resolution point of view. And this is our publication on Applied Surface Science, where we explain what we see with aluminum, for example. It's quite different from it. This happens. This is a similar process with all the metals, but in the case of brass, copper, silver, gold, you can introduce nanoparticles into the glass. But with aluminum, they react and they form an aluminum silicate glass type material, which forms a waveguide, a sort of buried waveguide into the material. You can see we have the plasma plume with excited species bombarding the glass from below. But since we can have a high resolution spatially and from the timing point of view, that is with the type of pulse duration that we choose, this is the type of laser we choose, then we can play around with this and have very good, we can do very good spatially resolved waveguides in any transparent material, for example. And here we can see that we can penetrate up to, for example, with silver, up to 80 or 100 nanometers inwards into the solid transparent substrate. This is how we explain how we have this waveguide on the right. The one on the right is with brass, but we have seen the same with aluminum. And this is the mechanism that we explain, or the schematic of the mechanism of how this aluminum silicate, which is amorphous, forms inside of the glass. Then you can also do with copper, silver, and gold, you can do some plasmonic layers within the glass inside, so they are protected from the environment. And you can write, as you see there on these letters. These are all written by the same, with high resolution, with the same technique. You can see in the center how it is carried out. You can see the laser goes through the glass and it evaporates the metal into the glass. So in the end, we have a permanent layer, either of nanoparticles embedded in this glass substrate, or as you see on the right, a layer of metal on the surface of the glass, which is conductive. So that is how you can see the result. We proceed so we don't get too late. This is the latest publication we have on this technique. It was just published in 2021 in Applied Surface Science, led by Professor Angurel, which you will hear later in a lecture. And here we have the same type of system with a picosecond UV picosecond laser, which has let's say a pulse duration, which is quite convenient to avoid damage to the glass. And this is the type of mechanism that you can expect from what is done here. If you have a single shot, laser shot, you get what you see on the left, this type of circular deposits on the glass. If you make two of these spots, you get the next one. If you make a line, you get this more complex line, although it's a series of combination of circles, as you see before on the two previous figures, but it becomes almost a line. And as you move it towards one side, or you move the sample on the opposite direction, then you can have a very nice layer of a coating left behind in the direction of the sample movement or in direction contrary to the laser movement. And so this is what you can expect from single pulse effects. As you see here, you see the deposit around in a circle type geometry. And as you move the sample, then you can see, you can look on the top right micrograph, you can see the deposit is left behind. So you can get a nice deposit, and you can do this in the whole sample, or you can do it with high resolution, moving the beam along the sample. And this is what you see on the cross section of these. So you end up, I don't think we can see it very well here, but essentially you have nanoparticles on the inner part of the glass, and you have a deposit outside. And this depends on the laser parameters and the associated experimental parameters used to deposit this. And if you want to make a deposit which is conductive, you can change the resistance depending on the laser parameters. Particularly, if you look at the pulse repetition rate and at the speed with which the laser scanning is carried out. And you can see that in some way we can design the resistance of these layers of metal. So this would be very valuable to make this type of circuits, interdigitated circuits. And so with this, you can see on the right on this video that we can generate DBD plasma, a dielectric barrier discharge plasma, which has many applications nowadays. And so this is done just with this method. So this is a very interesting application that we can have to generate different types of geometries and optimize DBD plasma devices. And here you can see a picture where in the dark, where you can see nicely how this is lit up between two interdigitated electrodes that we put on a glass substrate. So let me conclude with this. And I would say that in laser-induced reverse transfer, or laser ablation backwriting, or laser ablation or laser backwriting deposition is a complex ablation deposition process. It combines ablation of metal targets with writing of previously deposited, but I don't think you can see this, layers. It can be carried out at room temperature and ambient pressure in air. It's a fast, dry process, which gives you directional, spatial, and time control. And it can produce nanoparticles inside the glass substrate or metal layers outside it, which are perfectly integrated or unintegrated at the atomic level. And it enables printing of robust metal electrodes for the electric barrier discharge devices with any desired geometry and directly over the glass without any chemicals in a dry process. And it is limited, unfortunately, to transparent substrate combinations, which can be glass or single crystals. And just to give you a quick overlook, if I have still some time, Becky, do we still have some time or not? No, it's your microphone is off, so it's.
Yeah, still you have approximately 10 minutes.
Okay, so we will finish very fast. So I give time for everybody else. Okay, so this is just an idea of what we do in the group. So we use lasers to melt materials at room temperature or in an invention that we have, which is called a laser furnace, especially for ceramics and glass, which are prone to thermal shock when there is when they suffer important temperature gradients. So And on the other hand, we use ablation or non-ablative procedures when we want to do surface desorption, which is cleaning, laser ablation backlighting, or laser induced reverse transfer, as I presented in this lecture. Surface structuring, as you have seen also, to change colors, nanostructuring, and in situ reactive coatings, or also selective oxidation, as you saw in the titanium colors. And you can see this last publication and this laser-induced reverse transfer technique in these papers. And I must thank my colleagues who are written here in this transparency. And thank you for your attention, and also thank our financiers, which are these groups from the European Union and from the national and local governments. And with that, I thank you for your attention.
Thank you, Herman. Is there anyone for question? I cannot see the persons being in hall. Thank you, Herman. Is there anyone for question? Have you persons being in hall? Thank you, Herman. Is there anyone for
I could not hear I could not understand.
Who is talking? We never hear you. Just close to the microphone.
It's in Istanbul Hall, but
we never see.
No, but it's just that I could not understand the question.
Also, me too.
Unless there is something on the. Let's see if it is on the. Could it be on the?
Sorry, is there anyone in Istanbul Hall for asking something?
Let's see. Maybe I can see, or if you want, you can put it on the chat.
But nobody.
No.
Still. I think the camera system is not working over there, and the voice system.
The problem is the sound is difficult.
Yeah, because of maybe they are talking a little bit far from the microphone.
But I think maybe everything was clear, so there are no questions.
Yeah, of course, every time. Anyway, I think they can make a contact.
They can ask me. They can contact me anytime. Yes.
Yes.
Of course.
Still, we are here till last speaker. Then maybe they can connect and ask something. Or
no problem.
Yes. Thank you, Herman.
Okay. Thank you. Thank you very much.
Okay, you can get out from the.
Yes, I already finished the presentation. Yes, it's out.
Just now, I would like to invite Idris Tuğrul Gülenç. Do you hear me? Okay,
yeah. Can you hear me?
Okay, thank you. And he will talk about the in situ SEM stretch testing to evaluate wear mechanism of titanium carbon, titanium aluminum, vanadium nanocomposites manufactured by selective laser melting.
Yes.
Same subject.
First of all, the topic is different. Actually, we had sent two different presentations, and this is the title of yesterday's presentation, and today is a slightly different title, but it's again on selective laser melting. It's not totally different. Just to note, I will give the details. So give me a second. Let me just share my screen. Not this one. Okay. Let's make it full screen, and it should be here. Yes, it is here. Okay, I think you can see my screen right now. Can you? Can everyone see my screen right now? Yes, we can see it. All right. Okay. Thank you. Thanks. Hello, everyone. Thanks for coming for my presentation, and also thanks to organizing committee for inviting me for this talk today. My talk today will be about in situ X-ray microscopy tensile testing of titanium 6 aluminum for vanadium alloy parts manufactured by selective laser melting. There was a slight miscommunication for the schedule. So the talk titled with in situ SEM scratch testing to evaluate mechanisms of titanium carbide reinforced nanocomposites were yesterday presented by Beverly. You can go back and watch this one if you want to from YouTube records. This talk will be about X-ray microscopy testing. Quickly, let me introduce myself. I'm a postdoctoral research associate at the University of Sheffield. Right now, I'm working in the Nanolab group together with Professor Beverly Inkson. And this talk involves some studies made by a master student in our group last year. So, okay, yes, can go. Great. So here's the outline of my presentation. So I will just briefly explain why we did this study, what was the motivation behind it, how we made parts for selective laser melting, and what was the X-ray microscopy setup we used, and in situ rigs we used for these tests, and which sort of results we get from these tests, and why they are beneficial for us, and conclusions. So let's start with the motivation. Additive manufacturing is a quite popular method. Most of the researchers are aware, I'm sure. But the biggest problem with additive manufacturing is the porosity of parts. And this is the biggest drawback and biggest challenge for their widespread usage. Some ex situ tests are done widespread to evaluate their mechanical properties, but these are only let us to do some post-mortem examination after finishing everything. However, how pores are moving, how cracks are starting, how materials are deforming in real time sometimes matters more. For this reason, we decided to do some in situ micro CT tensile test. What we did is we did some tensile testing on a small sample, and we did the imaging at different loads while applying these loads at constant levels. And I will explain this in detail in the upcoming slides. So we also wanted to see, yes, in yesterday's talk, Beverly talked about some nano titanium carbide particle reinforced composites. We are also interested in how these particles are affecting the crack initiation, or if they are affecting this. But in this talk, it doesn't involve this part of this research because it hasn't been finished yet. This part also hasn't been finished yet completely. But I mean, this was also another motivation, how third particles, how composites are behaving differently if another particle is added to the matrix structure. So for selective laser melting, for the rig we used Debin in situ XRM rigs. We used a specific sample shape required by the equipment. So because titanium is not transparent, too much transparent against X-rays, we used as small as possible sample to get a good image. Additionally, the rig we used had an upper limit of 5,000 Newton force. So because titanium is a strong material compared with polymers or other metallic alloys, we made the cross section as small as possible. Therefore, we choose a small sample. Here is the sample's cross section. It's 2 by 2 for the thinnest part, and these are just to fit the rigs we used during the tests. And we made 3 of these ones for these tests. And for the X-ray microscopy, some of you may aware, some of you or you may not aware, there are some axes as well for X-ray microscopy. And also axis is important for additive manufacturing as well, because for additive manufacturing, grains are not equiaxial. They have a columnar. Electrically manufactured alloys has columnar grains. So therefore, okay, just back on mine again. Therefore, the axis we manufactured these materials are also important, because porosity, mechanical properties, grains are changing according to the build direction. I used a universal coordinate system for all this research. So during the whole talk, the coordinate system will be presented in this way. So the z-axis shows the build direction axis. I mean, this is the base plate on which materials were made and cut using EDM from the base plate. And z-axis is the axis coming to the screen side. And x-axis is the tensile test axis, and y-axis is the narrow axis. And I will show why these are important, why these matters in upcoming slides. Okay, so for selective mesomatic process, we intended to see how cracks are, how materials is deforming under load. Therefore, we need some pores to observe. Ti64 is one of the most widespreadly researched alloys for additive manufacturing, particularly for selective laser melting. Therefore, these material can be processed quite dense. But if it's dense, we were not able to image any pores at all. Therefore, we choose the high energy density window. So with this slow laser scan speed, 620 millimeter per second laser scan speed, we try to create some keyhole pores. These are pores mostly came across due to high energy density and evaporation of the metals and the evaporation pressure on the meltable. So therefore, we use the high energy density. In 190 watts laser power, we used 620 millimeter per second laser speed and 64 micron laser hash distance we used. So for these ones, for these parts, because we just did this test in as-built condition, we did some counter scanning. I am telling this because this affected the porosity of the part significantly. We will see in the external results. So therefore, this is important stuff for us. So we did first the initial hatch scan. We filled the part using continuous hatch ones, and after that we did contour scanning for each layer. For the contour scanning, we use a higher laser speed, 140 millimeter per second. This was the defined processing parameter in the software NetFab we used to prepare these files. And the distance between contour scan and the hatch scans are 190 micron. This was also default by the equipment itself. So we used a X-Radia 620 X-ray microscope. What makes this a microscope rather than an X-ray device? It has some objective lens. Below is the interior space of this X-ray microscope. There is the X-ray sources, and X-rays are coming. This is our sample, and here you can see the in situ rig we are using, and I will explain this in more detail in upcoming slides. And here is the objective detector. We have different objectives here to change the magnification, and this makes it a X-ray microscopy and change the magnification we can achieve. So there's a turret system there, and it changed the magnification, and there is also a lower lens objective to increase field of view as well. So by the way, I will talk about voxel size. What is voxel size? Because people not familiar with micro CT may not know what is a voxel. Voxel is actually a pixel, but in 3 dimensions. So on the image lower right hand side, you are seeing a pixel. So these are 2D ones are pixels, but if we make this a 3D cube, it becomes a voxel. Because this is a 3D scanning method, in X-ray CT, we are using voxels instead of pixels. We are using in 2D images. So 2 different voxel sizes used in this study, 11 micron and 3.5 micron voxel size. Voxel size is important for us because it defines the minimum feature size we can image, and also it defines maximum field of view we can image. If we choose a smaller voxel size, the field of view we are imaging will be smaller, but for large voxel size, it will be larger, but we will not be able to see small details with a large voxel size. So this is the limitation, and we'll talk about the effect of this stuff in the slides as well. So what the rig we used for this test was made by Devon. This is an in situ ring. So we are placing our samples. This is our own test sample between jaws of this test rig. The outer cage is transparent to X-rays, this outer cage. And by the movement of the lower jaw, we can apply either compression or tensile test. In this example, we did tensile tests on these samples. So we used we did this test on 2 samples. One is in 2 different loads. One is unloaded condition, 2200 Newton load condition, and 4400 Newton load condition. And for the other one, it is 2000 Newton and 3800 Newton. And I will explain why we choose these different load conditions in the upcoming slides. So after we did the test, we are getting this XRM data, and we use Dragonfly software to analyze this data, to create pause in 3D, to analyze data, to examine the statistical data from these images. So here's on the left-hand side is the TIFF files we obtained from the scan, and on the right-hand side is the outer shell of the part and showing some pores in it. So this is what we are achieving after XRM scanning, and this is the thin part of the sample we scanned in our experiments. So first of all, I want to compare how X-ray microscopy is useful to examine surface structure of the SLM parts. On the left-hand side, you are seeing the scan made with 11 micron voxel size. Because it's 11 micron, it doesn't show details that much better, as good as like the 3.5 micron one on the right-hand side. For SLM, there are some hatching to produce material. So each single layer is scanned by successive laser scans, and the distance between these laser scans is named as hatch distance. So for the top surface, there are some laser scans on the top surface, and this one is a optical profilatory image. I put this one because this is on the same sample. This shows what is actual surface morphology in 3 dimensions. So on the left-hand side, we are barely seeing some laser tracks on the surface, but they are not visible really well. This is mostly because of 11 micron voxel size, relatively large voxel size, and 64 micron was the hatch distance. But for this analysis, I just, to reduce the noise, I removed all the features small. I removed all the features smaller than 10 voxels. So therefore, something smaller than 100 micron is not visible easily in these ones. But I mean, 100 micron in 3 dimensions. Don't think about the one single dimension. So we are barely seeing some linear lines, but it's not that much useful. But if we choose a small voxel size, we are able to see the surface structure quite clearly. These small bits on the surface are partially molten particles, mostly sputtered particles, actually. These are happening due to this because laser is scanning a powder bed during the manufacture. Some small spatters are jumping to the surface, so they are solidifying on the surface and creating some partially molten particles. And even these small partially molten particles are visible if we choose 3.5 micron voxel size. And this is quite representative for the compared with the optical profilometry. And also there's an optical image as well, just to have an idea how the surface looks like in the actual image. So we also examined the side surface. On the left-hand side, again, we are seeing this side surface. On the left-hand side, we are, okay, I just shut down my video. Yeah. On the left-hand side, we are seeing the side surface for 11 micron voxel size. Again, there are some parts, especially for side surfaces, because it's embedded in powder bed during the manufacturing these parts. Side surfaces are full of partially molten particles, but we are barely seeing some of these particles, some signatures of these, but they are not that visible. But in an optical profilatory image, they are more visible. But in actual optical image, optical microscopy, which they are really, really well visible. With X-ray microscopy, actually, side surface is even better than optical profilatory, because for optical profilatory, we are sending lights and they are reflecting from the surface. Because of the rough surface or roughness of the side surface, most of the light cannot scatter back to the sensor again after touching to the surface. So therefore, the steep sides of these surfaces cannot be visible with optical profilatory. But for X-ray microscopy, side surface is quite well defined because X-rays are going through this material. So if the voxel size is small enough, we can see the side surface in a really well detail. And I would say this is the best detail for the side surface we can see right now. So let's move on. Tensile test results. So this is the first sample scanned with 11 micron voxel size. So I want to remind again the axis of these parts. So x-axis on both here on these XRM images and on SLM build directions, they have the same axis. So on both images, x-axis is this axis, z-axis is the build direction in both XRM images and both SLM builds. So we are seeing some poor population around the edges of these parts, because we did counter scanning and we used a high energy density for inner parts, but we didn't manipulate the counter scanning accordingly. This created a poor population around the edges of these parts. So these parts are colored for the position on the y-axis. The red one is the y-axis here. So sorry, the colors here and here are different. I just realized that the colors are for the y-axis. So the purple ones on the left, yellow ones on the right, as you can see clearly. Well, I mean, there's a clear population. Additionally, there are some some poor population between layers because of high energy density. Keyhole poles are distributed between layers, and we are seeing from the top view this time. This is z-axis, and we are looking from the z-axis from the top view. These are x and y-axis. We are seeing here. Red one is the y-axis and blue one is the x-axis. So again, we can see the poles distributed alongside these edges due to contour scanning. But if you look from the top, the y-axis doesn't change, doesn't cause any other change. But in the z-axis, we are seeing some keyhole pole population at some certain distances. So at different loading conditions, after thresholding these, we created some 3D poles. And we image pores in different conditions. First, unloaded conditions. Actually, it's not unloaded. We applied 10 Newton force, just too little force, just to make it stable during the scan. Unloaded condition, 2200 Newton load condition, and the broken condition. I'm saying broken. We didn't intend to break the sample. Normally, the expected ultimate tensile strength for Ti64 alloy manufactured by SLM is somewhere around 2000 megapascal. So we choose a load of 4400, which is quite close to this because we want to make some plastic deformation as well to be able to observe the crack initiation. However, probably due to the high population of the pores within the sample is just cracked earlier than we expected. Therefore, we did the first scan in unloaded condition, second scan in 2200 Newton condition, and third scan in the broken condition. And I will just compare these porosities in upcoming slides. So first of all, there's a difficulty for X-ray testing of these parts because we are doing 3 different scans in 3 different loads. Field of view is changing slightly. We are doing all the best efforts to not to do this, but it's changing and it's not available in most of the cases. Therefore, we have to align features for some reference. And also material is being deformed and these features are moving alongside the material for different loads. So what I did is, because you are seeing 3 different colors here, the yellow one shows the unloaded condition, the red one, yellow amber color. I mean, it's not actually yellow, but it looks like a yellow one here. The reddish one is the 2200 Newton load condition, and the purple one is the blue one is the after broken condition. So I just aligned pause at the end of the broken condition, and I aligned 3 different the pause of 3 different load conditions: unloaded, 2200, and broken condition on these square on the left hand side. As you can see here, all the pause are really well matched to each other. But if we go to the right, we are seeing a switch of the pause to a higher degree. What I did is, and here you are seeing the other piece of the broken material, because after being broken, we imaged this part, and the other piece of the broken part only was in the field of view, but unfortunately, the rest of it was not in the field of view. So what I did is just match this side, match the distance of pause on the left-hand side, and to measure how they switch to the right-hand side on the right after the test, after different load conditions. Here you are seeing after these features calibrated. I also used the outer shape of these parts to align these features together. And you are seeing how it's deformed. This red one is the original in, 2200 Newton condition. So it's quite deformed after the test. As you can see, in this one. So here, this image is the magnified view of this little square here. So here, let me open my points. Yeah, it will be easier here now. Okay, the image show in the next page shows this square here. So we are seeing some pore shape. As you can see, the red ones are 2200 Newton load condition, and the blue ones are the broken condition. And pores are moved for some distance. What I did is, because we know the voxel size, we can measure everything we imaged using Dragonfly software after being sure they are aligned according to Faucher. This is the most painful stuff of this work. So the distance for the pores to move, I mean, I choose the ones closer to the edge because these should show the maximum movements relative to the base material. So they moved something around 340 micron. Bear in mind, this is not under the load. I mean, this is broken, the load was just removed, but the red one is still under the load, it's not broken. So because it's not under the load, the sample just released some of its deformation, some of the elastic part of its deformation. Else normally I would expect a higher deformation range here if the sample were not broken during the test. So this sample was broken. The sample just moved. These pores are moved at the broken edge, somewhere around 340 micron. So if we assume, because it looks like this part could be the crack initiation point. So if we choose this side as the crack initiation point, to be honest, it's impossible to know what was the crack initiation point at that stage because it was already broken and we couldn't image the other half. But the examination shows this is most like the side of the crack initiation point. So it just cracked somewhere around, okay, my webcam just stopped again. Okay, this one again. So the crack should start somewhere around here on the right-hand side. This discontinuity on the surface is likely to cause a crack on the surface, and this crack may go through because this, if you can see this discontinuity on the surface, it probably moved into the 400 this side, and this is somewhere where the crack probably started during the test, and it just moved alongside this and caused some further cracks, and pores are just joined together. And this point also showed with a blue circle here on this red point. This red one is the 2200 Newton load condition. So it's not too obvious, but 2D images is more obvious, this discontinuity here. So this is why I just choose to show this one in more detail. All right. So yeah, these points, yeah, I put the square there. This point shows where potentially crack may start during the tensile test. And like I said, this is moving 400 micron, or slightly lower than 400 micron to front. And around this point, this may start any crack initiation. So another useful stuff about the X-ray microscopy is we can analyze these pores for different statistics. For instance, center of mass. What I mean by center of mass is for different axes, because we, as you can remember, we had different axes there, X, Y, and Z axis. So we had a population of pores closer to the edges because of the counter scans. So we should see more population around the edge. The population of the pores should be higher if we look at from the y-axis. So if we look for the center of mass of these pores from y-axis, this shows where is the center of these pores. We see a more higher population around the edges of these materials in unloaded condition. In a higher load condition, there's a slight shift, but still for the right-hand side, we are seeing higher population of these pores. Another useful statistic we can use is phi. What is phi? Phi is important for us to understand how pores were elongated in the structure. Phi is the degree of the longest axis of these pores in relative to the z-axis. If it's 0 degree, these pores are parallel to the build direction. If it is 90 degree, they are perpendicular to build direction. So as you can see, most pores are perpendicular to build direction. I mean, they are not perfectly perpendicular, but they tend to be more perpendicular to the build direction for all load conditions. But with the higher load, we are seeing more pores are elongated perpendicular to build direction. This makes sense because we are also applying tensile and the x direction, so this should cause some elongation of these posts. So this is why we are seeing here as well. So also aspect ratio is something important for this. We can image as well. So for the as built condition, the blue one solves as built condition for all of these graphs. By the way, blue one is as built condition. I mean unloaded condition. Sorry. The green bar is 200 Newton condition, and the red one is the broken condition. So for the aspect ratio, after it's under load, aspect ratio may slightly increase, but I mean it's hard to conclude some sort of aspect ratio, and it even lower down if we break the sample. If we were able to image this sample before the breakage, I believe we would see something different and probably more useful results. So let's have a look for the smaller voxel size experiment, 3.5 micron voxel size. For 3.5 micron voxel size, we are imaging these pores in a much more better detail. And we are by the way, the axis is again the same for this one, X, Y, Z, and it's the same for both SLM processing and X-ray microscopy. We are seeing again a higher population of pores around the edges, but we are seeing a less population of keyhole pores around the middle. The reason is that the keyhole pores are not homogeneous within the structure, and we are imaging quite small area in this one. The field of view is quite small because of smaller voxel size. We are still seeing some populations, as you can see, but it's not that much. I believe it's probably because of the smaller field of view of this sample. So again, this time, because the sample was broken earlier than we expected last time, we choose a lower load condition as the maximum this time. We use unloaded condition, 200 Newton. Again, with unloaded condition, we use something between 10 to 20 Newton as the initial load, just to keep it stable, keep the stage stable and sample. And for 200 nanometers and 200 Newtons and 3800 Newtons. And these are our scanning positions. So we are stopping experiments around these positions. And I mean, we are scanning our samples at that position, applying the force, stopping here, scanning again, applying force, stopping here, and scanning again. These changes of the force should not mislead you, because we are applying a 10-minute setup time, settling down time before scanning this, to avoid any movement of these samples, because if these move during the scan, we will get a quite bad image quality after the scan. So this is because this is a quite small voxel size. The field of view is really small. Therefore, we are imaging a really small area, and it is really hard to image. And because of this small viewing area, the field of view moves between samples because of deformation. The yellow one here shows the contours of the unloaded condition. Red one shows the borders of the 2000 Newton condition, and the blue one shows 3800 Newton load condition here. So these images are matching, because I just matched pores on the lower side, again on the left hand side, and you can see the pores are matching here, but if you go to the right, pores are deforming, but the area we can image are really small. It's just a few millimeters because of the small field of view. We are seeing a relatively small movement of the pores. This little tiny pore is the one here, because as you can see, the unloaded condition is on the quite left hand side. 2000 Newton load condition is slightly moved, and at 3800,000 it's just moved quite right way, but it's just 45 micron movements. Again,
Last 5 minutes.
it's about to finish. Thanks. So again, here we just checked the same statistics. The center of mass is again distributed alongside the edges, but it's moving because part is moving, and there's a slight shift of the positions. And phi is the degree is the particles are getting more perpendicular to build direction, more parallel to the tensile direction, similar to the previous example. For the aspect ratio, we didn't see again more significant and too much correlation, but there's a slight increase to a higher aspect ratio, but it's not. It will be too easy to conclude there's a significant improvement. So we should do more tests to say something more meaningful. So to conclude, X-ray microscopy is a really versatile method for characterization. We can characterize, and with the in situ rig, we can characterize deformation, pores, and movement of pores. And also, X-ray microscopy can be used to illustrate surface structure of these parts. Voxel size is a really important part of the X-ray microscopy. It really defines, because as you can remember, the difference between 11 micron and 3.5 micron, 3.5 micron voxel size was really good representative for the surface, but the field of view was really small and the results we can get were really limited. So there's a trade-off we have to make. It depends on the aim of the scan. And field of view is something really important to consider all the time. We must consider field of view. And these pores can be used to track deformation, how the parts are being deformed, what is the effect of, how is the change of pores deformation. And various statistical data can be extracted from these images and can be used for further analysis. This is still ongoing research. We are still analyzing the data, and we are right now analyzing individual pores, and we are trying to track and analyze these ones. So I hope this will bring more interesting results in the future. Thanks for listening to me, and thanks for your time.
Thank you, Idris Tuğrul. Is there anyone for question? Who? Luis?
Excuse me?
Who is asking?
I don't see anyone, I think, in my view.
Ah, there, I heard some voice, but nobody.
I think, yeah, microphone is for everyone. It's just muted right now.
Yes, but I am asking the people being in Istanbul Hall. Is there anyone for asking something in Istanbul Hall? Okay, thank you, Idris, for this good presentation.
Thanks for having me, and thanks again for the organizing committee for this opportunity.
Thank you. Okay, now I would like to invite Luis. Do you hear me?
Yes.
Okay, your turn.
No?
Yeah, because Andres is not here. I have not given a coffee break because we are still waiting in our room. No need for coffee break. Do you agree? Okay, you can start.
So,
If you want, we can give 15 minutes for coffee
okay, it's up
because
to you.
your time is a little bit late. And you can make maybe preparation.
No, I have this ready. You want, I can do it now.
Okay, start.
Can you see the presentation?
Yes.
Okay. So first, I would like just to thank all the organizers for giving me this opportunity. Just to, sorry, I'm going to. Okay. So I would like to thank the organizer for giving me this opportunity to show you one of our last results in laser sound melting process for fabricating manganese iron spinel ferrite. This is a work that has been in collaboration between the Instituto de Nanociencia y Material de Aragón and a group of Professor Bekir Ovselik of Sukuroba University in Adana. I'm going just to describe briefly which is the interest of this research. Then I will describe you the laser furnace technology that we have been using for preparing these materials. And the third part of the talk will be based on the sample fabrication. And I'm going just to finish giving you some ideas about the properties and the microstructure and properties of these samples. Iron-based magnetic spinel ferrites with a general formula A iron 2 oxygen 4 are extensively used in many sectors, as for instance in energy-based research, environmental application, as for instance in purification of water and soils, also in medical application as therapeutic and diagnostic agent or biological imaging or magnetic resonance imaging, as drug delivery, hyperthermia, or for instance for catalysis. This is just some examples of the interest of these materials. So they exhibit very interesting magnetic properties are also has been used in the shape of nanoparticle for a number of applications in bioscience. For instance, in agriculture, spinel ferrites have been proposed as keeping agents to deliver payloads or fertilizers or chemical into a specifically location of the plants. In order to process a ceramic sample using a magnetic furnace, we need to have in mind that when you apply a laser treatment, you are inducing a high thermal stress on the sample, and due to the properties of this material, these thermal stresses can induce some cracks and can induce the fracture of the sample. So, in order to avoid this, we have proposed a technology in which the laser process is performed while the sample is placed inside a furnace at high temperature. In particular, we use a roller furnace that allows you to move the sample inside the place at high temperature, and then you can apply a laser. In this particular case, it was a CO2 laser because also the system is used for processing glass and another ceramics that can only absorb the CO2 radiation. And as you can see in this video, when the sample is in the high temperature region, you can see clearly how the laser can induce the melting of a very thin layer of the material that you can move through all the surface of the material due to the rolling system of the furnace. In consequence, you have a geometry in which the laser it makes on top of the surface a line that is perpendicular to the direction of the sample movement. Moving using the movement of the system, then you can translate this molten zone through all the surface of the material, and you can see usually when you have after the solidification process takes place, usually the solidification front induce some microstructure on the grains you are obtaining after the laser treatment. So usually you have on top, very close to the surface, a material that is resolidified. Obviously, below this material, you have another region that has been affected by the laser treatment because you have reached very high temperatures. and below that you have the unaffected substrate. With this system, we have built some, we can call some semi-industrial prototypes that we have been used for the different applications in the framework of several European projects. The first one was the laser firing live European project. In this case, we use a 15 meters long furnace and 2 laser systems in order to be able to process bricks for 4 sizes. Okay, so the difference with this can I have showed you before is that you can go with a laser from the upper part of the material and another system from the bottom part, and you can see here that you are able to process the material, okay, or the ceramic, in this case, the bricks in 4 sides. So with one laser, you use, for instance, the front and the upper part, and with the other laser, you process the bottom part and the back part of the brick. Sorry, but I cannot see now moving here. Also, in another European project, we developed a second semi-industrial prototype. In this case, was a 13-meter long furnace, and the system was optimized to process flat samples. In this case, with a width up to 60 centimeters. And in particular, the system has been developed to process ceramic and glass, has been in some collaboration with companies that work in the sector of ceramic and glass. Here you can see some of the samples we can process, so we are able just to control the material you put on top of the ceramic substrate. You can see on the left figure, and if you see on the right, you can integrate high temperature materials on the surface of a glass, and for instance, to improve the decoration possibilities you have for making new pieces of glass. Also, this technology has been used to implement some kind, we can have called a 3D technology for the fabrication of very dense ceramic materials. In this example, I have shown to you is just an alumina zirconia eutectic, and as you can see here, we have been processing, for instance, sampling with 3 different laser treatments. The first laser treatment has been applied on a press substrate of the ceramic material. Then we we apply a coating of the ceramic or powdered ceramic on top of this. We apply again the laser treatment, a coating, and then we can repeat the process several times. So here you observe the surface of the eutectic. Clearly, we have started with a mix of alumina zirconia powders, and clearly you can see that we have integrated this and we have obtained the structure of the ceramic, of the eutectic ceramics material. Also, you can see that we have avoided the creation of cracks, and the aspect of the material is very dense. If you look to the cross section of this material, also, for instance, in the left part, you can see how was the microstructure after the first laser treatment. Clearly, in the bottom part, you have the powders of the mixture of the alumina and zirconia powders. And on the top part, you can see the molten and solidified region that it is very dense, and you have the eutectic ceramic. For instance, in this case, we have been using we have obtained a 400 micron thick layer of eutectic ceramic. And if after repeating the process 3 times, we are reach near 1 millimeter of the ceramic mat or the dense ceramic eutectic. Also, this was in 2 years ago, we started to process also some spinels. In that case was a nickel ferrite spinel. And here you can observe the microstructure of the surface of the sample before the laser treatment, in which you can clearly observe the nickel oxides and iron oxide particles. And in the left part, you can see how the sample surface is after the laser treatment. Clearly, you have a very dense material with very big grains, and we have created a spinel after the laser treatment. So now I'm going to describe you what a similar process from the magnesium iron oxide spinel. So the process is as follows. So first we fabricate initial pellets by mixing the oxide powders. Then we develop the spinel phase using a laser treatment at high temperature. And in these cases, we have been applying these spinels to fabricate nanoparticles using the ablation process, as Professor Osseli has to show you this morning. In order to fabricate the manganese ferrite spinel, so we take the stoichiometric amounts of magnesium oxide and iron oxide. Then we mill, and after in distilled water, and after the slurry is dry, we have pressed, and we have obtained usually 3 millimeter thick and between 15 and 20 millimeters in diameter samples, as you see here in the photograph. In order to fabricate the spinel, we have used the laser furnace treatment in a 4-meter long roller kiln. In that case, the CO2 laser is at 350 watts. The maximum temperature we can apply to the sample is 1,200 degrees, and the processing speeds are between 1,000 and 4,000 millimeters per hour. In the case of the experiments for the spinel, we have used a temperature of the furnace at the central point of the furnace of 1,000 degrees, and the processing speed of this was 1.5 meters per hour. The laser scanning speed in the perpendicular direction was close to 60 meters per second. So the idea is that the laser moves very fast in order to maintain stable the molten volume in the full width of the sample. In principle, I will show you examples with 3 samples in which we have processed 3 different laser treatments. In this laser emits like a duty cycle process, in which it means that the laser is on a half of the period, given percentage of the period, and is off the rest of the period. You can see that, for instance, in manganese 1 sample, the sample is on only 40% of the period, 20 microseconds over 15 microseconds, while in the other 2 samples, the time the laser is on is 50% of the period, 25 microseconds. Longer is this period, is this time, stronger is usually the laser effect on the sample. Because when you reduce the dot cycle, you have more time to cool down the sample. The difference between the 2 samples that we have processed with the highest data cycle is that in the case of manganese 2, we have the laser scans a life of 70 millimeters, while in the 3rd sample, this line is shorter, so it means that the time the laser is on the sample is higher. So in principle, the idea is that the strongest laser treatment is in the case of manganese-3 sample, and the lowest laser treatment is in the first one. Okay, you see that near more or less the conditions from sample 1 and 2 are very close. In the case of sample 2, only 80%, 70% of the we have an increase only of 70% of energy, while in the manganese-3, this increase is 72%, 70. You see here the difference in the samples. First, when you look to the aspect, clearly the amount of molten material in the first sample was much lower than in the third sample. That clearly you see here an effect much higher. Even that, we have measured with a pyrometer the temperature on the surface of the sample, and you see that the temperature was of the order of the temperature you have the liquid. So it's approximately 1,500 degrees. So it means that we melt, we have the liquid phase, and obviously with the composition we have applied after solidification, you have the spinel phase. Here you have the cross-section of the samples. In the case of the first sample, you see that the first thing you can observe here is that the magnesium oxide particles were very big. Usually we have particles higher than 100 microns in size. This means that it takes more time to melt this, to have a uniform melting and to allow to homogenize the composition in all the liquid phase. In spite of that, and you see in these photographs that we have been able to obtain more or less a layer of 70, 100 microns thick, in which the sample has been melted, and after melting, you have a uniform liquid phase. When we go to magnesium-3 sample, in which we have applied a 72% more energy to the system, you see that the thickness of the area that has been melted is higher, and is more than 3 times higher. Also, you observe that the grains have a growth habit with a given angle. That this is more clearly observed when we will see the surface of the sample. Here you can see a profile, a composition profile of the distribution of iron and magnesium and going to penetrating into the surface, into the sample, sorry. And clearly you can see that on the molten material, more or less the composition is constant and with a value very close to the spinel 1. And inside the sample, clearly you can see the magnesium oxide particle, the big magnesium oxide particles. When, as I told you, when we look to the cross-section, then one thing we can see is that we have 2 different types of grains. In the case, you have one grain in which we say that the microstructure has a laminar structure and with a given angle. Just remember that when we were looking in the cross-section, we saw that the grains have a given angle, a growth habit with a given angle. But also, you have some grains that grow near parallel to the surface of the sample. This is also observed in the case of the sample processes with a high energy. But in this case, what we have observed is that the growth habit is separated in different domains. So in one part of the sample, most of the grains are parallel to the surface of the samples, and in other part of the region, we have accumulation with grains that grow with a given an angle in comparison to the surface. Okay. If you look to you analyze, for instance, in the case of the sample with a low energy, and in which we expect to have a lower homogeneity in the composition of on the liquid, clearly you can observe that some of the grains in which you have a more planar structure, they are grains that are mainly associated with iron oxides, and while the grains that grow perpendicular to not perpendicular, but with a given angle to the sample surface, we are very close to the spinel. Also, we observe some grains, as in this case number 3, in which you observe that the main component is the manganese oxide. This could be, the origin of this is that there is always some of these big grains that were in the precursors we have not finished to melt completely, and obviously we start to diffuse some iron inside the magnesium oxide, but we have not completed the transformation. This is, for instance, the case you observe in the grain that we have left with the number 3. Okay. If we reduce the magnification of the photograph, so we see more an average measurement of the composition, then you see that we are very close to the ratio of the spinel. Okay, but it's important to have in mind that in this case, with the lowest energy level of the laser treatment, we have not been able to maintain, to homogenize completely the liquid phase. Okay. Also, you have something similar in the second sample, in which also we observe this difference between one region and the others. But when we go to the third one, in where the amount of molten material is much higher, obviously here you can observe that the distribution of magnesium and iron oxide is much uniform in the case of the areas that we have a very flat surface and with the composition close to the spinel. And also, we have a more uniform distribution when we see the other grains in which the growth habit is not parallel to the surface, but we have some orientation in comparison with the surface of the sample. Okay. Also, we have performed some magnetic characterization. Here you have the hysteresis loop we have measured in the samples at 10 Kelvin. Clearly, we have a soft ferrimagnetic behavior in which you can see that both the magnetic saturation and the coercitivity field increase when we increase the energy of the laser treatment. So that means that we improve the homogeneity of the liquid, and also we improve on the quality of the spinel phase we have obtained after the laser treatment. If you do the same in the case of you observe the behavior of the sample at 300 Kelvin, you observe a super paramagnetic behavior, and also the magnetic the magnetization signal you measure is near 2 times higher in the case of the sample that was processed with the high energy than in the other two samples that were processed with very similar level of energy laser. Okay, so just for conclude, yes, I think we can say that the laser melting technique facilitates the production of spinel materials, but in general, it facilitates the production at high temperature of any kind of ceramic material, avoiding the generation of cracks during the processing. And this possibility opens the new fields in the sense that you can process ceramics with a very dense very dense materials, ceramic, and you can avoid the crash generation on them. Okay, these materials has been produced for or have been used for substrate for nanoparticle fabrication using laser ablation. And yes, I would like to thank the person that we have been working in this project, and also I would like to thank the institution that has financed both in Spain and in Turkey that has financed this research work. Okay, thank you for your attention.
Thank you, Luis. I wonder, is there any question in Istanbul Hall? Istanbul Hall sent several message. No. You have changed, I think, the presentation, Luis. This is the new version of presentation.
Yeah.
Okay, I want to see. Just send me, please,
Okay.
because you made some good slides. Then we can discuss later on for publication. In this case, with the new version, we can prepare easily.
Okay.
But in this time, we should give a charge to Herman. I hope. Herman, do you hear me?
Yes, yes.
We give a charge to you for new manuscript. You know, it's very nice presentation.
Yes, very nice from Luis. Excellent.
Excellent presentation. Okay, thank you. Now let me call. Okay, Andres has already come. Let me give microphone to him. Andres. Andres, do you hear me?
Yeah, yes. Do you hear
Okay,
me?
you came in time.
Of course, I'm always ready.
Okay, now your turn.
Oh, I should start already.
Yeah. Just because one of the speakers has not participated, and no coffee break because we are still in computer.
Yeah.
In front of computer, and now your turn. Just you can start if you're ready.
Okay. Just prepare this. Okay. Do you see?
Yes, we see and hear you.
Okay. Thank you for your presentation. And I would like to acknowledge the organization of the conference for their kind invitation for this conference. Well, I'm going to present something which sometimes we reach a crossroad. So we have to decide, because sometimes we are making research for publishing, for getting good results, but when we have to fulfill the requirements of the companies, sometimes we are not in the same way. So I think we are going to see this during the presentation. So first of all, I'm going to outline my talk, which will be divided in 5 points, which are the introduction, where I'm going to present something about the thermoelectrics, their applications, and why they are interesting for our normal life. Then I will enter in previous studies and data we have obtained, because this is a very long range project. So we'll see how the techniques, the materials are going to evolve during this time, following with the new objectives, mainly directed by the companies, and the path we have followed to reach these results, which will be discussed afterwards to finish with some conclusions. Well, when we think about the energetic situation we are facing in our normal life today, we can see that most of the energy we use as primary energy to produce electricity, to produce a movement in the automobile or transport, most of it is wasted in form of heat. Only about 34% of the energy we use is efficiently used. So this 66% energy loss is a huge amount. This is due to the low efficiency of this kind of systems, which make we are emitting a lot of greenhouse gases, and much more when we take into account that 66% of this primary energy could be avoided. So one solution to improve these systems is harvesting this wasted heat. For this purpose, we think about thermoelectric harvesting of this energy. It should be said that this is not a new technology. Really, it has been used for years, as I am going to show you before going on. And for example, when we see the Voyager 1, everybody knows about this satellite. Mostly, if you see Star Trek is coming back in many, many years, but it has been launched in 1977 and is still working right now. More recently, we have the rover Curiosity, also working with thermoelectrics. New unexpected mission to Titan, the Dragonfly, will be, if everything goes on, will be in 2034. And this kind of systems, as well as the polar lighthouses in Russia, they are working from the 50s. Right now, they are abandoned after the fall of the Soviet Union. All these systems are working with what is called radioactive thermoelectric generator. For the thermoelectric materials to work, we need one heat source and is produced by radioactive disintegration of radioactive materials. They produce the heat, and all these machines are working. On the other hand, also we have a thermoelectric watch, which is working with the body heat. No need of batteries or movement, so it's working alone, just with the heat of the body. Only it is stopped working when we are dead, where no heat is produced. But in order to explain how these kind of materials work, we can think about a normal material where we can see the charge carriers, and when we hit one part of this material, charge carriers move from the hot to the cold side of the material. This is producing a temperature difference between the two ends, and this temperature difference is inducing a voltage difference. The relationship between this voltage and temperature is called the Seebeck coefficient, which is usually expressed as microvolts per Kelvin. If we consider that most of the thermoelectric materials are semiconducting, we can find whole conduction where the charge carriers are whole. So we have a voltage where the negative charge is at the hot side, and they are called p-type. When we use as charge carrier electrons, we have the opposite voltage. And this is influencing the Seebeck coefficient, as for p-type is positive, and for n-type is negative. All these materials can be evaluated through the so-called figure of merit, CT, which is composed of the Seebeck coefficient, working temperature, electrical resistivity, and thermal conductivity. The most known systems working with this kind of materials are in metallic ones. When we consider thermocouple, the voltage is changing when the temperature is changing. In the case of we need generate energy, the system is a little bit more complicated. We need two types of thermoelectric materials, P and N type, which are electrically connected in series and thermally in parallel. When we get this situation and we apply some heat, what we produce is electrical power. For this purpose, we can consider many different materials. For example, in this table, you can see different kind of materials with their working temperatures. Usually, when the material has higher CT, the performances are better, and usually is considered for practical applications to have CT higher than 1. This is very rare in this kind of materials. We can find in this kind of materials, but they have a problem. When they work at high temperature, they can be oxidized. Also, you can see bismuth, tellurium, so scarce materials and very expensive. So for massive applications, they are not the good ones. So we have to consider more environmentally friendly materials as the silicides and the oxides. But when we consider we have to apply this to the market, we have to think about the prices. And as you can see here, when we think about, for example, silicide, silicium germanium, the costs are much higher than the oxides. So this is the main reason we have been working in oxides, because they have more or less good thermoelectric properties together with low costs. So concretely, we are working in calcium 3, cobalt 4, oxygen 9, which can be written in this form because it is composed, is a crystalline structure is monoclinic, but composed of alternate layers, the cobalt oxide and calcium cobalt oxide with different structures. This cobalt oxide with a cadmium iodide-like structure is the conducting plane. While in the center, we have rock salt-like structure. These two structures have the same crystal parameters, A, C, and the angle beta. But they have different B parameter. This makes that these two structures are not fitting. So they are called misfit cobaltites. So when we consider this structure, we can say this is well known that this material is conducting by holes, so it's P-type material. The modification of this rock salt structure is going to modify the B1, B2 relationship between the two layers, so is well known to affect the Seebeck coefficient values. And taking into account this conducting plane, if we arrive to make a good grain orientation and increase density, we can decrease in an important matter the electrical resistivity. And why is because we are working with this material. If we see this table, we can see cobalt, calcium are abundant ones in comparison with antimony, indium, bismuth, tellurium, which are much more scarce. And we have decided to change the B1, B2 relationship by substituting calcium, but a larger alkaline earth cation, which is strontium. When we make this and work under normal ceramic route solid state method, we make only changing this relationship. It's the only thing we do. Calcium and strontium have the same oxidation state, so the only modification we are going to make in the structure is the B1, B2 relationship. When we do this, we start with a ball milling to mill the starting powders, then some calcination, cold uniaxial pressing to get the pellets, and sintering for 24 hours. When we do this, we get the material ready to be characterized. And if you want more details, you can find in this article. And what we have found, no significant microstructural changes. I'm not going to show, but when we consider Seebeck coefficient, we can see there's a slight increase of Seebeck coefficient, especially for the 007 substituted sample. But the values are very similar at room temperature. These similar values at room temperature means that no changes in charge carrier concentration. So the relationship between cobalt-3 and cobalt-4 in the conducting layer is constant. So this is important because we have confirmed the only modification is the B1, B2 relationship. When we study the resistivity, we can see an important decrease of electrical resistivity with strontium doping. It means that charge carrier move easily. We have a better mobility of the charge carrier and leads to the decrease of this electrical resistivity. When we combine these two results, we get what is called the power factor, which is the electrical part of the dimensionless figure of merit. So considering only Seebeck coefficient square and electrical resistivity. As we can see, 0.07 sample is the best one. So we take this composition and we keep in mind for the next works. So another question we have also started to make is modifying the initial particle size of this material because the lower particle size mean higher resistivity, higher reactivity, and so better phase purity, and we suppose better properties. For this, we have introduced a tritium milling, which is very easy to make. It's similar to the ball milling. The only difference is the size of the balls, and they are making in wet medium. So by friction between the balls and the powder, we get a very good reduction of particle size. The other possibility is making some magic. So we are going to prepare some potion to get good power, and of course, in this kind of materials, power factor. These two methods are co-precipitation using two different materials, ammonium carbonate or oxalic acid. It's much longer because we need make a solution of all the nitrates, so control pH of the solution, and then with these two compounds, we get the precipitation of all the cations mixed together. After that, we have to wash, we have to dry, and then decompose the organic material, and then all of them follow the same process, which is, again, calcination, uniaxial pressing, and sintering, again, in the same conditions, just to avoid to have different conditions for the previous studies. When we do this, we can see the difference of the particle size. This is after calcination. We have a co-precipitation, very small particles. We have also the other co-precipitation. The shape is different because crystallization is different after calcination. We get after a tritium milling and comparing the classical solid state. As it's possible to see, we get much lower particle size. But when we make sintering, we can see they grow not so much as the solid state, but all the particles are growing. When we consider power factor, we can see solid state is much lower than the other two, and even attrition milling is slightly lower than the co-precipitation. This is due because a better mixing of cations in the co-precipitation methods. So what we can extract from here, lower grain size we get, better properties we can expect. And this you can see, if you want, in this other publication. Well, still, we are going to try to improve materials. And now we have to keep in mind texturing of this kind of materials we make by hot uniaxial pressing, where this ceramic material uniaxially pressed in form of disc is put between two silver layers, and we put pressure and temperature, and we get this grain orientation and grain growth, as we can see in this image, before and after hot uniaxial pressing. We can see density, grain orientation has been improved in an important manner. This has been done following this recipe. We can say we make ball milling, calcine, uniaxially pressed, sintered, and then hot pressed. When we do this and we see increasing density, increasing grain orientation. So it is expected to have a drastic decrease of electrical resistivity. And when we make this, we can see the difference between a sintered material and a hot press material. In this regard, we have get about 6 times higher than the sintered materials. And this was the highest power factor obtained in the literature. In the literature, it was about 0.45. So nearly 3 times higher than the best reported in literature. So the highest obtained so far you have in this article. The only problem, difficult to measure thermal conductivity. We have got some more or less result about 4.5 watts a Kelvin meter, too high. But in any case, when we think we have a good result, we talk with a company and they say, oh, very nice. But it's too expensive because too many steps, too long time thermal treatment. So this is not good when you want to think about practical applications. So we have decided to take all the data we have obtained before and coming to try to reduce times and cost in these materials. So we have started to make micrographs of the initial mixture of the powders after ball milling and after attrition milling. When we see this, we have been able to reduce the time. Attrition milling and ball milling is the same. Calcination, 24 hours. We need just one. Pressed and pressed, the same. Here we have eliminated the sintering before the hot pressing, but this is still 12 hours, while here we have only 1 hour. What we get is some difference, much larger grains in the case of the ball milled materials, which is normal, but the orientation is approximately the same. With this, and we compare the results, we can see slightly better with the attrition milled samples, but we have reduced a lot of time. So this has been published in this article for more details. So when we use attrition milling, we can reduce the thermal treatment in around 97% of the time. But the power factor has been reduced about 37% with respect to the maximum value of 1.13 we have shown before. But still we have problems. We are using silver. This is an expensive material. So we have to try to eliminate it. For this purpose, we have evaluating temperature and pressure and using graphite instead silver. So we have changing temperatures, pressures to see how the thermoelectric properties are going to be developed. When we consider different temperatures at the same pressure, we can see that the grain size increases with temperature and also the grain orientation. And it is very clear that we can reduce electrical resistivity. On the other hand, when we change pressure and maintain constant temperature, we can see the same evolution. Grain size is increased and also grain orientation and also resistivity, very similar to the previous graph, as we can see there. So when we see the minimum electrical resistivity we have obtained in this test is around the best reported in literature for this kind of materials. Also, with this, with the objective of the practical application of these materials, we have studied mechanical properties. With 3-point bending tests, we have seen that increasing temperature or pressure, the flexural strength is increased. The same is happening with Vickers micro harness. So in any case, higher temperature or high pressure are increasing mechanical properties. And the values are the best reported in literature for this kind of materials. Going on with the study, we have considered thermal properties. What we have seen, no clear variation with temperature or pressure in the thermal conductivities. You can see they are very close, but the difference we can see here in the linear expansion coefficient, which is very important when we consider to use them combined with another materials in thermoelectric modules. It is clear that it is decreased with temperature and pressure. And finally, when we consider the Seebeck coefficient at a constant pressure, we can see it increases with temperature. Also, to make a small summary of these properties, we can see the minimum thermal conductivity at 800 degrees in two different samples, 1.51 and 1.53 watts Kelvin meter in two different samples, the minimum linear expansion coefficient, but the highest Seebeck coefficient is in this other sample, which is higher than most reported in literature. But coming to these thermal properties, they are lowest than the best reported in literature. So when we still going on and study what happens with the power factor as a function of pressure or as a function of temperature, we can see that power factor increases with temperature, with entering temperature, but also with applied pressure. So this is important because when we seems to be not so much differences, but when we compare the results in the highest and the lowest temperature and pressure conditions, we can see the difference is important. It's about 2 times higher when we compare to the other one. And now coming to the things we have seen, because in the previous study we have said we are around 0.7 in power factor, and here we have still decreased. But the important thing, we have in a first step, we have decreased 37% of the power factor. And still here we have another reduction, about 25%. But the good thing, we have decreased 97% of time. And when we change silver by graphite only in silver cost, we have decreased 99% costs. So this is very important reduction in cost when you think about practical applications. But finally, we have decided to see what happens with the dimensionless figure of merit. And what we can see when we combine power factor with thermal conductivity is that we are in a maximum of about 0.35. And it seems not so much when we need about 1. But this is the highest reported in literature. And the curious thing, the best result is in 900 degrees, 61 megapascal. It's not the highest pressure we have used, because with higher pressure, we get better power factor, but thermal conductivity is increased. So in combination, we can use these conditions and get a reduction very important in the cost of the materials. Still highest reported in literature so far. So it's not so bad as we think. And finally, as a summary, we can see that the isovalent doping has been shown to increase thermoelectric properties, as well as the decrease of initial particle sizes due to the enhanced reactivity. Hot pressing allows grain orientation and increasing thermoelectric properties. We can reach 1.2 milliwatts Kelvin square meter as power factor when we combine isovalent doping and hot pressing, but when we have to decrease the time and the cost, we can reduce to 0.7 and 0.52. But CT is the best reported in literature with a very short time processing and very low cost because we have eliminating expensive elements. Mechanical properties are the highest reported in this kind of materials. When we avoid talking about nano indentation or things like this, but in micro hardness or mechanical bending, it are the best. And thermal expansion is very good because it's the lowest reported in these materials and is much closer to aluminum oxide, which is used as cover in the thermoelectric modules. So will allow to last much time because we'll be reducing thermal stresses between the different materials forming these modules. Okay, and thank you for your attention.
Thank you, Andres. Let's have a look whether there's a question in Istanbul Hall. Is there anyone for asking question? I think no voice. Thank you, Andres, again.
There is no question.
Okay.
Thank you.
Okay, there's a question. Andres, don't go.
Okay, okay.
Just ask. Okay, is it possible to see you or?
You don't see me?
No, we see you, but I'm asking to question the person. Okay, waiting for your question.
Actually, we don't have any questions. Thank you for the presentation. Thank you.
Okay, thank you, thank you.
Thank you.
Is there anyone waiting for us? I think no. There's only Andre and Anatoly, but they are not here. Maybe we should wait a little bit because their connection still we have a time according to the schedule of conferences.
Becky, I think it's a problem to go so much ahead of the schedule because people come at the right time.
Yes, yes.
And also we need to go to the bathroom.
Yes.
So
Let's
I
go.
think
Maybe
don't be so energetic and respect the time more.
But they have called me and suggested starting earlier than the expectation time.
But
because
also
of-
Anatoly and Andrei.
Yeah, we will wait for them because still we have a time, about 1 hour for their connection.
But still, Luis has to talk.
Yes,
Luis talk. Luis has
exactly.
already
That's why I
talked.
say he was so energetic.
Okay, this is
Still, we have 3 persons. Anatoly, Andre, and Juhal. Maybe they will
Okay.
participate.
so I can close presentation
Yes,
and everything.
finish. Yes, yes.
Okay. Okay, thank you.
Thank you, my friend. Let me look. Let's meet somewhere in hall.
Yeah. Okay, I will go out.
Okay. Hello, Andre.
Hello, Vikir.
How are you?
Nice to see you.
Yes,
Very nice.
yes. It was nice to see you again.
Yeah. So long time. So we were basically out of communication because of known problems.
Yes,
Yeah.
because of the pandemic situation, we, this is not the problem, but we couldn't contact again. And past 3 years, and you know, I was organizing conference each 2 years.
2 years. Yeah.
Yeah, but now I have to cancel because of now I have been living in Zaragoza. This week is the last week days for me. I have been living here for 1 year.
So you're really going to Andres, yeah?
Yeah. No, not Andres. Together with a group, Herman and Luis Alberto.
Okay.
And also with Andres, we are producing both thermoelectric samples and the nanoparticles from spinels by using ablation technique. Also, we have already produced big size visco sample for electrical application like a fault current limiter, the others. Now I came to the end of the project. Next week I return to Turkey. My son will stay here. you know, maybe.
Yeah. So the life keeps moving, yeah.
Yeah. Now
Yeah,
he was at these conferences, gave a talk face to face. Now he's in Turkey. He will return next week. And now waiting for the conference time today. I have been waiting for Siderenko, Moldova, but he has not participated yet, just before you.
Yeah. So I assume that I'll be the only one, yeah?
Yeah. No, still.
No.
Herman is waiting, Luis Alberto, and somebody in Istanbul hall, but I have not seen them because no camera connection to them. Maybe we can start if you want to, if you are ready.
Yeah, sure.
Okay, now Luis over there. German also there.
Herman, nice to meet you again.
Hello.
Sorry, my microphone was off. Nice to see you.
Yeah, it's a problem of this online conferences. So if you have anything with a connection, that's because it happened even at university. We have cuts which cannot be predicted. It's difficult to be safe from it.
Yeah.
So when this thing happen, we are off.
Now the problem is, I think they are giving at the same time a live connection to YouTube. Therefore, we are getting in trouble to connect into hall because of the two types a live connection. There are two types of a live connection.
You mean it takes a lot of traffic?
Yeah, because of traffic. Maybe that is the reason. Because now it's giving in a live in YouTube channel.
Okay.
They are registering later on. If somebody wants to watch again, they're finding the speaker and select the time exactly and listen again. This is the reason we are sometimes delaying.
Yeah. Well, okay, if
you can start.
It's possible, yeah,
you can start. If Anatoly arrives at, then we can give later on the chance for talking.
So I guess you can see my presentation, yeah?
Yes, we are seeing, no problem, and hearing you.
Okay. Oh, it's not that I want. Good afternoon to everybody, to all colleagues, and first of all, I would like to thank the organizing committee for inviting me, giving this nice opportunity to participate in this conference. And also my personal greetings to Bekir, the chair of this session. So in this presentation, I decided to focus more on some specific processing approaches for advanced thermoelectrics, and this work was performed in our group during last probably 3-5 years. and also involved a number of collaborations which I would like to acknowledge. So greetings from Aveiro, Portuguese Venice, very nice place. As you can see here in this place, we are doing our research on thermoelectrics and some other things. And this city also attracts quite a lot of tourists. And so if one day you'll come to Portugal, I think it would be a nice place to 1-2 days stop to spend some time. So let's now speak about thermoelectrics. I know that Andreas Sotelo already, previous speaker, already gave let's say introduction to this concept, but I'll repeat some things. So basically the thermoelectric, the Seebeck effect could be in simple way explained like this. So if the charge carriers in any semiconductor would behave themselves as a molecules of ideal gas, so what will happen if we'll hit one part? So they will get more energy from the hot part and they will move to the cold side. In this case, this way we can get the potential difference, and eventually, if we are able to maintain the temperature gradient, we can generate electrical current, electrical energy. So this is the same for p-type semiconductor. The only thing is that the discharging is opposite, and eventually we can combine this two parts in one couple like this, and this is basically a unit of thermoelectric module. And these modules, they potentially can be used for harvesting the waste heat. As you probably know, a huge amount of energy is produced worldwide, but around 60% of this energy is lost as a waste heat. And of course, if you can convert at least part of this energy back to the electricity, it would be very nice. First of all, let's just a few words I forgot to say. So in our group, we are working on this part. So this is the functional part of the thermoelectric module, so-called thermoelectric legs, and we are developing the materials for these legs. So waste heat, from where it comes and where it could be considered potentially promising for thermoelectric applications. So we have different primary energy sources like petroleum, coal, natural gas, whatever, many things, and then can be used directly in different sectors like transportations, industrial, residential, commercial, and they can be used directly for electricity generation. All these uses are associated then with some rejected energy, which is mostly waste heat. So the highest amount is corresponds to electricity generation, then followed by transportation and industrial sectors. So we can assume that thermoelectrics could be probably interesting for these areas, but we need to take a look closer to the type of waste heat. So here you can see the sectoral shares of the waste heat with different temperature. And what you can see that electricity, although it generates really huge amount of waste heat, mostly the temperature is below 100 degrees C, so it's so-called low-grade heat. In opposite, for transportation and for industrial sectors, you see that they generate significant fraction of high temperature waste heat, with temperatures above 300 degrees, and this is already interesting. So why it is important to have higher temperature? Probably you know, so if we are converting the temperature difference into electrical energy, so this is basically Carnot efficiency, yeah? So at the highest the temperature difference, the highest conversion efficiency. That's why for electricity, for example, the amount of energy rejected is huge, but Carnot potential of this energy to be recovered is very low. While for transportation and industrial sectors, this is higher, and that's why we can consider that probably thermoelectric technology would be most promising for these sectors. So since we are speaking about conversion technologies, we must talk about also conversion efficiency. Conversion efficiency is proportional to, this is the term of the Carnot efficiency, as you see, and there is one more parameter, so-called ZT, dimensionless figure of merit, which is linked to basic materials properties like electrical conductivity, Seebeck coefficient, and thermal conductivity. Thermal conductivity in turn consists of two counterparts, electronic and lattice. And this part of the product of electrical conductivity and squared Seebeck coefficient sometimes is called the power factor. And this is basically the electrical performance of thermoelectric material. So to have higher efficiency, we need higher ZT. So the challenge looks very easy. We need to increase design material in the way to simultaneously increase electric conductivity, Seebeck coefficient, and to decrease thermal conductivity. But in fact, it's not so easy because all these parameters are interlinked through the charge carrier concentration. So we introduce charge carriers. Okay, the conductivity is increasing, that's fine, but at the same time, we have simultaneous decrease of Seebeck coefficient, and after certain charge carrier concentration, we also have significant contribution of electronic counterpart of the thermal conductivity. So basically, after, let's say, design of our material, we can end up with even lower performance than before. The maximum ZT actually is can be observed only in very narrow range of the charge carrier concentration, and it's not always easy to find this this optimum. Oxides have emerged as promising thermoelectric materials as well. Also, for a long time, they were considered mostly useless for this purpose. Let's take a look at this graph. So here the graph compares ZTs of oxides with ZTs of other promising thermoelectric materials, promising in the sense of intermediate and high temperature application. So zinc phases, half-Husserl, silicon germanium alloys, silicide, some other composition. And you see, whenever we are shifting to the right side, temperature increase. So what is left here is only oxide materials, so green parts. And there are no other materials. The problem is that they are not stable, or they cannot operate under, let's say, ambient conditions in air, I mean high temperature. And all oxides are left. However, as you can see, also the performance of oxides is quite lower than compared to those reference thermoelectrics. In fact, during the last 5 years, probably significant progress has been achieved with values reaching almost 1.5, which is really impressive for strontium titanate composite with graphite. But generally, if you look at this here, so you can see that normally the values are still below those characteristics for the reference high temperature materials. So let's try to do some simple SWOT analysis of the oxide thermoelectrics. So their obvious strengths are large Seebeck coefficient. They are thermally and chemically stable. They are pretty abundant in nature. They have mostly lower toxicity than other materials. And also, what is important, as I said, there was significant progress demonstrated during the last 5 years. So the weaknesses are also well known, this low mobility of the charge carriers due to mixed covalent ionic bonding, and also in many cases relatively high thermal conductivity. So the threats are mostly related to the device fabrication, and here we can speak about high contact resistance in modules, and also cracking during operation cycles, because as we are speaking about high temperatures, and of course, oxide, they have different thermal expansion behavior compared to typical construction materials, like, for example, steel, etc. But fortunately, there are also opportunities. So first of all, the oxide, they show good prospects for high temperature harvesting. We can think also about all oxide modules where all components are oxidized. In this way, we can minimize this compatibility issue. And there are also three opportunities which I wanted to touch a little bit during my presentation today. This is redox and structural flexibility of oxides. Also, different processing approaches can actually be applied to this material, which is not very common. And oxides are also very flexible for different composite concepts. So one of the things I wanted to speak is the laser processing of oxide materials. Today, during session of today, there are already speakers speaking about laser processing for other purposes. So it is really a very, very popular thing. So here we use this technology for growing thermoelectric materials. We have two rods made of precursor of our material, molten zone formed by laser irradiation. These standard fibers of the target materials can be grown in different direction with different cooling rate, and also what is important, in different atmospheres. So our camera allows this, and it's actually very interesting. And in this way, we can prepare materials from different thermoelectric oxide families. When we want to predict so just some existing and expected advantages of such kind of process. First of all, laser processing allows high density of ceramics. And it is very important also from the viewpoint of mechanical properties. It is also crucible-less processing. It doesn't require to have a crucible. It creates unique redox conditions, allows processing of refractory materials like oxides. Today, laser is also not something very exotic, I would say, and also different options are available, like electrically assisted laser floating zone, gas atmosphere. And we also can think about one more advantages, because actually we can grow these legs, which are almost or completely ready to be installed into the thermoelectric module. So this is the direct and very fast process. Associated bottlenecks are problems with growing incongruently melting materials, and we'll see this next example. Formation of some non-equilibrium phases, radial heating uniformities, instability of molten zones sometimes. And we also should take into account specific laser type, specific material requirements. So material must, in fact, absorb the laser irradiation. When we want to predict the composition of our material after growth, so let's take an example of this known 349 phase calcium cobaltite. So we can use phase diagrams. We should remember that phase diagram, they refer to thermodynamic equilibrium. And here we're speaking, in case of laser processing, we are speaking about strongly non-equilibrium conditions. But we could expect that in case of this material, so where the frozen phase composition, which will be frozen after laser growth, will be this. And indeed, it happens. So the S-grown fibers represent basically a mixture of calcium oxide and cobalt oxide. So to turn this material to be thermoelectric, we need to perform quite long annealing in air, because the stability region of 349 phase is very narrow, and upper temperature limit is relatively low. So the diffusion processes are quite slow. And this could be shown by this microstructural evolution. We see this S-grown fiber, which have very nice structure, this columnar structure with cobalt oxide and calcium oxide. It looks very nice, but absolutely useless in terms of the thermoelectric properties. And then after some intermediate time of annealing, we're starting to have 349 phase, still having some amount of simple oxides. And then eventually, after this long time, we have this typical microstructure of 349 phase. So what is the impact on the electrical performance? Here I put just some literature data, and this red curve corresponds to the conductivity of our fibers, 349 phase grown by laser. And so what you can see that our results are somewhere on the borderline between conventional processing methods and some specific method like spark plasma sintering and hot pressing. So in case of Seebeck coefficient, the situation was a bit more complex, but still we have some quite comparable results. And in terms of the general performance described by the power factor, you see here, so we are again somewhere in the borderline between the conventional processing and spark plasma sintering hot pressing techniques. So not so bad, but the advantage is not, again, not so very large to say that we really can get outstanding results using laser floating zone. So what about other families of thermoelectric materials? Here I'm showing the results for manganite. They are another promising family of oxide thermoelectrics. And here the desired perovskite type calcium manganite phase is formed immediately after laser growth, which is it's here, yeah. And this is very good, of course. Bad thing is that we cannot actually, even after quite long and treatment at high temperature, we cannot get rid of this these impurities completely. And this really complicates the situation with manganites as well. So here you can see the S-grown fibers with clear typical structure after laser growth. But then after the milling, we still have quite noticeable chemical contrast and different phases. However, we also found out some interesting microstructural features like dendrites, but dendrites is something quite typical for laser processing, and formation of such core shell structures with the shell and the core having essentially the same chemical composition, but the shell has has much higher electrical resistance. Probably it's not so useful for heat harvesting, but we use this kind of core shell structure now to develop some thermoelectric sensors for flame detection based on this microstructure. Sometimes we are finding things which could be potentially interesting for other applications. Another thing is that there is a very obvious effect of the cooling rate on the performance and the phase composition of calcium manganite-based materials. So basically the rule here that the maximum performance is observed at cooling rates around from 10 to 50, probably 100 millimeters per hour, because the higher cooling rates normally result in more phase impurities, more inhomogeneous phase composition, and then even after thermal treatment, it's difficult to re-equilibrate it. So what about the electrical performance? Unfortunately, the results here were not so good as for 349 phase. So again, I put some literature data, and you can see that the materials grown by laser, they have comparable performance in terms of electrical conductivity to the conventional samples processed by conventional solid state route. However, we consider these results quite promising, and also I mean promising in the sense the potential of the laser floating zone technique. We decided to build a thermoelectric module made of this laser floating zone processed calcium cobaltite and calcium manganite based LECs. This work was performed in collaboration with our colleagues from Institute of Solid State Chemistry from Russian Federation. So this module was designed for radial waste heat harvesting, and contains 12 couples, P-type and N-type materials. So in this concept, then the LECs are located in parallel to the heat source. The heat source itself is a tube, okay? But they probably logical would be to assume that should be connected perpendicular, but no, they are connected in the parallel way. And this design actually allows to have high specific power during to optimal positioning of the LECs in the space, in the volume, and also permits quite easy installation and replacement of the LECs. Here it's how this module looks like in reality. So these tubes are needed to cool down the cold junction. So the thermal imaging actually show that in this configuration, we can achieve quite notable temperature difference along the thermoelectric leg. So here are the results. The current voltage curves and the power. Basically, I'm not going deep into discussion of these results. They are disclosed in our recent paper in SAS Applied Energy Materials. So the output of this module was comparable to the similar modules in terms of the number of thermoelectric LECs from the literature. However, we expect a bit higher performance, and this is what is happening is that the output power of this module is significantly limited by high contact resistance and relatively low performance of N-type LEC. So just an example how you can spoil all the work by just We have only one part which is not functioning properly. And in any case, we are considering these results quite interesting. Believe that such module design and one-step laser grow thermoelectric legs could have some future, and could be this approach could be further developed. So just a few words about what we are going to do next in terms of the LFZ. We really consider growth in specific atmospheres. This is very interesting for strontium titanate and other titanate-based thermoelectrics. We need to optimize, of course, this procedure to have reasonable performance for the legs and comparable performance to be installed then in the modules. And also we are thinking about deliberate processing of the composite using laser folding zone, because during this method we have steep temperature gradients, and they can really facilitate dissolution, exsolution of different phases, and eventually result in microstructures with fascinating properties. In fact, the redox flexibility of oxides allows to play with composites and their microstructures, also in the case of more conventional processing methods. I want to talk briefly also about this. So redox flexibility, when I'm saying this, I mean the capacity for oxides to exchange oxygen with the gas atmosphere while maintaining the core phase composition, not without decomposition. And of course, this redox flexibility has is very important for such applications of oxides like electrodes of solid oxide fuel cells, and also in some catalytic processes. And it would be reasonable to assume that it would be also interesting could be used somehow for enhancing the thermoelectric performance of these materials. And one of such impacts was demonstrated in our earlier work dealing with the redox promoted strontium titanate-based materials. The idea behind was to use redox sensitive cations like molybdenum, which can be first introduced into the structure under oxidizing conditions and then exsoluted from the structure under highly reducing conditions. So it could be done by adding molybdenum oxide to strontium titanate matrix. Then after oxidation, we have such kind of phase composition where molybdenum enters the strontium titanate matrix and also forms different scheelite type phase. And then eventually, if we reduce all this together, we are ending up with this with such composites. The composite lattice, I will show you what it does mean, and also containing molybdenum micro and nanoparticles. So you can see here the microstructural evolution. So from oxidizing conditions to reducing conditions. So these red particles correspond to metallic molybdenum. And these metallic particles can be quite small, nanometric size. And another thing which we found out also is some kind of such atomic scale islands of strontium molybdate, this more yellow reddish part in the strontium titanate matrix. So, what I'm calling the composite lattice. So this, of course, these tiny inclusions at the atomic scale could be very interesting for suppressing the thermal conductivity and also for some other purposes. So all the and also confirm that a significant part of molybdenum is retained by perovskite lattice, by XPS. So all these microstructural effects, structural rearrangement of the composition, it has very interesting effect on the thermoelectric properties. So here is the matrix without molybdenum addition, and so when we add in molybdenum, we have a simultaneous enhancement in the power factor, although not very large, and simultaneous decrease of the thermal conductivity. So we believe that this is happening due to, in the case of power factor, it is due to enhancement of the Seebeck coefficient, due to some charge carrier filtering effect, most likely. And in the case of thermal conductivity, this decrease is associated to the phonon scattering and redox promoted interfaces. Now we are working on some new design principles of such composites. We already have indication that the improvement in performance could be much higher. So look at this situation. bit another way around, we can ask ourselves, is there any situation where adding of metallic metal like a precursor for cation and oxide would be advantageous instead of using, as compared to the using oxides or salts as we usually do during solid state process? And yes, there are some interesting situations. Again, the case of 349 phase, which is natural superlattice with promising thermoelectric performance, but a big problem with these materials. This material is a high grain anisotropy. It makes it difficult to densify. So normally, after conventional processing, this material is quite porous with a porosity level like 60%, 40%, something like this. And if we can find the way to put something which will close these pores and connect these loose 349 grains between themselves, probably we can expect some improvements there in the performance. Why not to use metallic cobalt? So metallic cobalt is chemically compatible with matrix, but how it could be done? So here our approach is the following. So we have a mixture of 349 with metallic cobalt. So what could happen on oxidation? The 349 phase, of course, remains because cobalt is, again, is compatible with that. And cobalt oxidizes and forms cobalt oxides. This process actually is accompanied by expansion. Expansion and cobalt oxide basically filling the pores and connecting the grains of 349 phase. Itself, it should be noticed that itself, cobalt oxide is quite good thermoelectric material, but here it works in synergy with the 349 phase. So this is, let's say, the structure of pristine material without any cobalt addition. And so we have cobalt addition, we have the formation of such structure where the grains of 349 phase are well interconnected in between them. And what is the impact on the performance? So here are the pristine material without any cobalt addition processed by a conventional route and very porous. And this is just another way, two-stage process to sinter 349 phase, again, without cobalt, or the same results could be actually achieved by laser processing. And if we apply the same procedure, sintering procedure as for this material, but to the material containing cobalt additions, we end up with this nice improvement in performance. Electrical conductivity, CBEC remains essentially the same. And we have the power factor values almost reaching dense material, which is prepared, which can be prepared by different methods, but not in the same way like this. So the reference. So this is basically the reference, the same sintering conditions as for cobalt. Any other involvement of oxidation reduction reaction for improving the thermoelectric properties? Let's try to look at another family of oxide material, zinc oxide based material, quite known, and you probably know that aluminum doped zinc oxide is a state-of-the-art thermoelectric material which can be used as a platform for designing various composites and co-substituted material. Normally, this material is prepared by mixing zinc oxide and aluminum oxide or salts. So what about if we use metallic aluminum as a precursor? We can also remember that the classical reaction, one of the classical reactions of aluminothermy, is reaction of metallic aluminum with zinc oxide. And this reaction actually results in evolution of significant amount of heat. And you can see this from this DTA curve for zinc oxide containing metallic aluminum addition. So the reaction starts at around 660 degrees, I think, yeah, the melting point of aluminum. And there is a significant heat flow because of this aluminothermic reaction. So we can expect that when we have this reaction inside of our material, it could somehow help to densify and also could promote doping of the zinc oxide with this with aluminum, because itself a Wurtzite structure is not very flexible like perovskite. A Wurtzite structure doesn't allow to enter more than let's say 1%, 1 atomic percent of aluminum. So normally by usual method, you can probably even put even less. It's difficult. If you have this local overheating conditions, probably it would work very well for doping itself as well. And so what we have as a result, so how we demonstrated it. So we used the model composition like this. You see the amount of aluminum is very, very small, and you cannot put a lot of more there, in fact. So we used conventional sample, which was prepared from using aluminum oxide as conventional precursor, and 2 samples which were prepared using aluminum powder, either nanopowder or micrometric powder. And all of them, they were processed absolutely under the same conditions. And here are the results. So you see the blue curve here corresponds to conventional sample, which was prepared from aluminum oxide as an aluminum precursor. And we have this improvement, or also some improvement in density in the case of material prepared using metallic aluminum precursor. But in terms of the electrical conductivity, the increase was quite significant. We also had some variations of Seebeck coefficient. Also, they're not very straightforward. In terms of the thermal conductivity, there were not so many variations. We didn't expect them because this is not kind of microstructural engineering. But again, remembering the results for electrical conductivity, so you can see that using this approach, we can improve a significant enhancement in the T values. So basically, 2 times higher performance at high temperature of the material prepared using metallic aluminum micro powder as compared to the conventionally prepared samples. So this, I think, this approach really opens different ways to design other materials and to use other metals. Also, keeping in mind that what we need actually is not exactly alumina thermic reaction. Probably if we can consider that the metals themselves, they will oxidize during sintering. Itself, this reaction is exothermic, and this could be also beneficial for doping zinc oxide itself. Okay, so just some final remarks. So oxide materials are indeed flexible for laser processing and allow this method allows to produce highly dense materials with a unique microstructures. But really, if we want to attain some high values of performance, we need to optimize carefully the laser processing conditions. We can also involve redox properties of oxides for tailoring their thermoelectric performance and design composite with high thermoelectric performance. And we can use also, in some cases, specific cases, metallic precursors instead of oxidized forms like oxides, carbonates, and nitrates. And this could offer some additional possibilities for structural and microstructural problems sometimes tuning. So some acknowledgements to projects, which some of them are ongoing, some of them they are already finished, but nevertheless. And thank you very much for your attention.
Thank you, Andre. Let me ask.
I think I'm in time. Yeah.
Yes, you are in time. Is there anyone question? As I don't know whether somebody is waiting in Istanbul Hall. Is there any question? Thank you, Andre. I think there is no question.
Okay. Thank you very much.
Thank you very much.
Have a nice weekend.
Keep in touch.
Keep in
please.
touch. Sure, Bikir.
Okay, thank you.
Thank you very much.
They say there is no question.
Okay.
Okay.
Okay, thank
now,
you.
See you later. Let me look. Is there anyone for waiting? Yusuf,
Yes, I'm here.
you are here. Will you talk or Zuhal will talk?
I will talk.
Huh? You will talk.
Yes.
Okay, but there's some problem. I think they have given more time for you. You are invited or normal speaker?
There's no email for invite.
Yeah, I saw. Okay, you are Turkish now. Nobody maybe.
6:35 geçe normalde başlıyor.
35 geçe de yok. Şimdi gelmeyince biraz sarktı zamanlar. 25 öyle var, 15 öyle var. 40 dakika vermişler sana da sen davetli misin? Normal konuşmacı galiba görüyorum burada. 15 dakika verdikleri şey yani.
Olabilir. Bilmiyorum ikisi arasındaki fark.
Yok, süreç açısından. Sen
Hı hı.
çünkü son konuşmacısın.
hı.
Başlayabilirsin. Bittiği yerde
Başlayayım mı?
bırakırız.
Tamam.
Okay, last speaker is Yusuf Gencer. He will talk about the solar energy forecasting using machine learning models.
Okay. How can I?
Just ekran paylaşımına gel yeşil altta.
Tamam. Tamamdır.
Okay.
Geldim. Can you see my screen?
Yes, yeah, we are seeing and hearing you. No problem.
Okay.
Start.
Okay. Let me introduce myself and my lecturer. I am Yusuf Gencer, and I'm from Istanbul Technical University Physics Engineering Department. I'm a student, and Zuhal Er is an associate professor doctor at Istanbul Technical University Physics Engineering Department. Also, she is my thesis subject supervisor. Our subject is solar energy forecasting using machine learning models. First of all, I want to talk about a little about photovoltaic panels. PV panels producing by semiconductor materials. Most commonly used material is silicon, and thanks to this structure of semiconductor materials, we can convert the sunlight to electrical energy. There is 3 common types for PV panels. These are monocrystalline PV panels, polycrystalline and thin film PV panels. Okay, we have a panel, but how can we calculate the energy production? There's a very simple formula for this. Only you need to know these 4 quantity. A is energy, E is energy, A is a total area of the panel, R is solar panel efficiency yield, H is annual average. But this calculation only for in the clear sky day, you can calculate your production. But if there is cloud or different other weather parameters, you cannot know exactly how much your energy will produce. Okay, why solar energy forecasting is needed? Our subject is based on this. It is essential for efficient management of the electrical grid and power trading. What does that mean? You can see on the figure, there's a microgrid structure. The distribution companies buy the electrical energy and distribute the consumers. Distribution companies meet the supply-demand balance, and for this reason, they should know how much energy they need to sell, and they will buy energy for that information. Based on the law, if you are renewable energy producer, you cannot sell energy without giving any information. You have to tell how much energy you will produce tomorrow, and when if you how you can forecast this producing, you have to use some software, and you can use on your own calculations. There's a very different methods, but if you ask me why you have to give information for tomorrow, because when you sell your energy For example, you said I'm selling you 1,000 kilowatt for tomorrow, but when tomorrow comes, if you cannot produce 1,000 kilowatt energy, you have to pay the gap between the difference, your produced energy and your promised energy. Why you have to pay this difference? Because the distribution company, if cannot meet the supply, should go to fossil fuel energy producer and buy energy for consumers. Why they are going to fossil fuel energy producer? Because this is the fastest way. This is your fault to unmeet the supply-demand balance. Now, solar energy forecasting is needed to decrease your loss, and you have to give minimum error rate to not lose your money. Okay, I will now talk about our experiment. This data set taken from the Enercast. Enercast is the company that gives the forecast for tomorrow, solar energy and also wind energy. This facility information I will give you. Nameplate capacity is 4,000. Weather data source is Icon EU Nest. This data source covers the Europe and Turkey, Turkey, and data based on UTC0. Model run they selected as input. Time range we selected is 4 years. These are the weather parameters: direct radiation, diffuse radiation, temperature, pressure, relative humidity, snow depth, cloud cover, wind speed, height above ground, 80-10. These are my input parameters. We try to understand which parameters affect more than others. First of all, we split the data set, train and test. This is, I don't know, maybe somebody don't know what is machine learning and how it works. In the machine learning, you need to split the data set into train and test data set. When you give the train data set to machine learning, machine can learn from the parameters how much energy will produce. And in the test data set, you are testing your model accuracy. In this meter data, we cannot use the 2015 because there's no humidity data for Icon EU data source. Okay, this is my this is our model information. ANN is an artificial neural network. It is working like our brain. There's a input parameters and output parameters. If you give some input parameters, you will predict what will in the output. I don't know, should I maybe I shouldn't stay long in this section. Just I want to say, with using ANN, with all parameters in the previous slide, with using all weather parameters, we reach the NRMSE value 7.90%. And with using only temperature and global horizontal radiation, NRMSE value is 8.33. And we decreased the NRMSE value for using all weather parameters. By the way, if you ask me what is global horizontal radiation, it is a direct radiation and diffuse radiation summation. Now, this is the result comparison of two different input parameters. As you can see, the blue line is meter data, the orange line is temperature and radiation, green line is all weather parameters when we used. If we use all weather parameters, there's a problem in the night hours. In the PV panel, you cannot produce energy in night hours, but if you put as an input parameter the other weather parameters, machine says there is a production in the night hours because machine learning still is like that. Okay, but why there's no problem in the night hours with using temperature and radiation? Because there is no radiation in the night hours, and global horizontal radiation is the biggest parameter for producing energy because it gives the information about how much solar energy. This is the random, this days chosen randomly to show the difference between the output values. As you can see, the green line can reach the top than the orange line. This is the decreased NRMSE value. Now, okay, I introduced you how ANN work and with other weather parameters, but what we did differently and how we decreased the NRMSE value in different way. This is our solution for decreasing NRMSE value more. Time interval selection methods. The day in the graph you can see there's a production, solar energy production graph in clear sky day. In the morning hours it is less, and the solar noon it is the very much according to other hours. And these intervals selected by using dynamically time interval selection based on the location of facility. We can know the sunrise and solar noon hours. These numbers -2 and +2 or 4 +4 choosing the experiment, this gives them better result to us. We try the different values and try the different intervals. This is the best one. And how it works, in the previous section I said there's ANN and how it works, but in this time we split the data into 6 time intervals. Each time intervals going to ANN separately, and each output collected separately and making one result. How it works best, because we saw that there's a difference characteristic in the hours. in characteristic of morning hours different than the afternoon hours. We saw that with using that experiment, and we decided to use that method. After that method, our NRMC value decreased 7.29. In this method, temperature and radiation 8.28 and all weather parameters without humidity 7.50. We saw in the correlation matrix, the humidity parameter has a negative huge effect on the output value. I mean, the production energy. We didn't use, so how will affect the humidity to decrease the NRMC value. You can see there is a 0.21% decrease with using humidity. This is the structure of our model. Now, this is the comparison results. Again, the meter data is the blue line and all parameters orange line. Radiation and temperature is green line. Without humidity is red line. As you remember, there was a energy production in night hours. We solved that problem with using that method, time intervals method. And with using all weather parameters, we can reach the top than using other weather parameters. As you can see, nearly this, we reach the top. And also, if clear sky days, we can estimate and we can forecast exactly, I mean, 99%, we can say, okay, that amount of energy will produce next day. These informations, next day energy production graph, and it made in 1 hour intervals. Yeah, we solved that problem and we decreased the NRMC value to 7.29. In traditional ANN, if you using traditional ANN with using all weather parameters, you will reach the 7.9%. And we decrease that with using time interval selection methods, it will be 7.29%. And that means you will not lose your money 0.7%. Our articles was like that. Thanks to Enercast. Enercast is the provider, the data sets, and they give us the data set and they give us their knowledge about this forecasting. Yeah, that's it. Are there any questions? I finished my slides. Thank you for listening, by the way.
Thank you, Yusuf. You are the last speaker. Is there anyone will ask question in Istanbul Hall? Okay. Yusuf, there is no question.
Okay.
Teşekkür ederiz.
Ben teşekkür ederim.
There is no question. Thank you, they say. Peki, teşekkür ederiz. Başarılar. Sen yüksek lisans öğrencisi misin?
Yok, lisans öğrencisiyim.
Lisans.
Evet.
Gayet güzel. Bu bitirme tezin mi?
Evet, bitirme tezim.
İyiymiş. Ben hocan katılacak diye belirtmişler ama senin katılman daha iyi olmuş. Niye? Çünkü biz gençleri daha çok
Hı hı.
cesaretlendirmek istiyoruz. O nedenle
Hocam da öyle istedi. Sağ
iyi
olsun.
olmuş, iyi olmuş. Yani şimdiden alışman iyi olur. Gelecekte akademik yaşantıda bunlara alışacaksınız.
Hı hı.
Ben de seni
Efendim, ben de hocası olarak öbür session'dan, oturum başkanlığından geldim.
hocam gayet iyi lisans öğrencisi olması iyi. Nedeni somebody is talking somewhere. Lisans öğrencisi olması gayet iyi dedim. Bu yaşlarda alışması çok iyi olmuş. Hocanı bekliyorduk dedim. Senin konuşman şey açısından hani cesaret olması, işte sunumlar hazırlanması açısından iyi olmuş dedim.
Yusuf'un ilk sunumu, ancak Yusuf'la gurur duyuyorum. Yusuf henüz mezuniyete biraz daha yolumuz var ama ilk etaplarda bu çıkışı yaptı. Yusuf geleceğin
Hocam
gerçekten mühendisi.
kendimi hatırladım. Ben 3. sınıf öğrencisiydim. Hocam bana demişti ki gel çalışalım. Tabii biz de başka havalardaydık o zamanlar. İşte geldiğimiz nokta burası.
Efendim şöyle söyleyeyim, biz derste tanıştık. Seçme dersimi alan ekibin içerisinde iyi ve kuvvetli bir ekibim vardı. Yusuf da onların pırlantalarına ödev vermiştim yapmaları için. Derste yaptığımız konuları bir şekilde uygulamaya geçiriyoruz. Onun üzerine çalıştık bu çalışmayı çıkartırken. Enarkas bize eksik olmasınlar bir ilgi gösterdiler. Yusuf'u staja çağırdılar, davet ettiler. Bu bizim için onurdur. Çalıştığımız bir konu şirketle örtüşmesi. Onlardan dataları aldık. Şimdi Yusuf onlarla devam edecekler ama Yusuf gerçekten geleceğim benim için onur duyduğum
Gerçekten hocam yani bu şeyde ben de yani şu ana kadar kendi üniversiteme, kendi öğrencilerimi bu yaşlarda bulup çıkartıyorum.
Aynen hocam.
Şu anda ben İspanya'dan konuşuyorum. Türkiye'de değilim.
Çok selamlar İspanya'ya.
Tüm öğrencilerimi de buraya hemen hemen getirmiş oluyorum. Çünkü
Şeref verirsiniz İstanbul'a da.
İnşallah hocam. Bu hafta son zaten bir yıldır buradayım. Haftaya döneceğim.
Selametle geldiniz.
İnşallah. Yani genç bir lisans öğrencisini görünce gururlandım. O yüzden biraz sohbet etmek istedim. Size de çok teşekkür ederiz. Böyle
Ben
çocukları
teşekkür
bulup çıkartmanız ülkemiz adına fayda
Çok
getireceğine
teşekkür
inanıyorum.
ederim. Gururlar benim için. Onlarla birlikte bizde kanat oluyorlar. Eksik olmasınlar. Bir şeyleri aktardığımızı onlar göstermesini yapıyorlar. Var olsunlar.
Teşekkür. Herman Luis, do you hear me?
Tamam.
Yes, hello.
Do you have any question to young student? He's an undergraduate student.
Very nice talk, and I'm not an expert on that, but I know it's very useful for us.
But in
And
this
for
age
many
and
things
in
we
these
do.
classes,
So
it was very fantastic presentation.
yes, excellent. Really
Thank
excellent.
you very much. Thank you very much. You are so
Yes.
kind. Thank you very much. I am glad to meet you.
Thank you.
Yes, my pleasure.
It's my pleasure.
So for the young speaker, that was excellent.
He's
And I think
so
it's very useful.
he's so powerful in science. So I believe that he will be achieved a good engineer in the future.
Yes, for sure. Yes,
Yeah.
and also this has a great future for us.
Yeah.
This type of technique.
Yeah.
Of
Thank you.
machine learning, and we need to implement that really.
Yeah.
Thank you very much. Thank you very much.
Okay.
Okay.
Have a nice day.
Have a nice day.
Have a
Bye-bye.
nice day.
Herman, I will shut down the computer. I am very tired now. I will pass in front of your room. I will say goodbye.